Lecture 5 of Our Knowledge of the External World as a Field for Scientific Method in Philosophy by Bertrand Russell. This LibriVox recording is in the public domain. The Theory of Continuity. The theory of continuity, with which we shall be occupied in the present lecture, is, in most of its refinements and developments, a purely mathematical subject, very beautiful, very important, and very delightful, but not, strictly speaking, a part of philosophy. The logical basis of the theory alone belongs to philosophy, and alone will occupy us tonight. The way the problem of continuity enters into philosophy is, broadly speaking, the following. Space and time are treated by mathematicians as consisting of points and instants, but they also have a property, easier to feel than to define, which is called continuity, and is thought by many philosophers to be destroyed when they are resolved into points and instants. Zeno, as we shall see, proved that analysis into points and instants was impossible if we adhered to the view that the number of points or instants in a finite space or time must be finite. Later philosophers, believing infinite number to be self-contradictory, have found here an antinomy. Spaces and times could not consist of a finite number of points and instants, for such reasons as Zeno's. They could not consist of an infinite number of points and instants, because infinite numbers were supposed to be self-contradictory. Therefore, spaces and times, if real at all, must not be regarded as composed of points and instants. But even when points and instants as independent entities are discarded, as they were by the theory advocated in our last lecture, the problems of continuity, as I shall try to show presently, remain, in a practically unchanged form. Let us therefore, to begin with, admit points and instants, and consider the problems in connection with this simpler, or at least more familiar, hypothesis. The argument against continuity, insofar as it rests upon the supposed difficulties of infinite numbers, has been disposed of by the positive theory of the infinite, which will be considered in Lecture 7. But there remains a feeling, of the kind that led Zeno to the contention that the arrow in its flight is at rest, which suggests that points and instants, even if they are infinitely numerous, can only give a jerky motion, a succession of different immobilities, not the smooth transitions with which the senses have made us familiar. This feeling is due, I believe, to a failure to realize imaginatively, as well as abstractly, the nature of continuous series as they appear in mathematics. When a theory has been apprehended logically, there is often a long and serious labour still required in order to feel it. It is necessary to dwell upon it, to thrust out from the mind, one by one, the misleading suggestions of false, but more familiar theories, to acquire the kind of intimacy which, in the case of a foreign language, would enable us to think and dream in it, not merely to construct laborious sentences by the help of grammar and dictionary. It is, I believe, the absence of this kind of intimacy which makes many philosophers regard the mathematical doctrine of continuity as an inadequate explanation of the continuity which we experience in the world of sense. In the present lecture, I shall first try to explain in outline what the mathematical theory of continuity is, in its philosophically important essentials. The application to actual space and time will not be in question to begin with. I do not see any reason to suppose that the points and instants which mathematicians introduce in dealing with space and time are actual physically existing entities. But I do see reason to suppose that the continuity of actual space and time may be more or less analogous to mathematical continuity. The theory of mathematical continuity is an abstract logical theory, not dependent for its validity upon any properties of actual space and time. What is claimed for it is that, when it is understood, certain characteristics of space and time, previously very hard to analyse, are found not to present any logical difficulty. What we know empirically about space and time is insufficient to enable us to decide between various mathematically possible alternatives, but these alternatives are all fully intelligible and fully adequate to the observed facts. For the present, however, it will be well to forget space and time and the continuity of sensible change in order to return to these topics equipped with the weapons provided by the abstract theory of continuity. Continuity in mathematics is a property only possible to a series of terms, that is, to terms arranged in an order, so that we can say of any two terms that one comes before the other. Numbers in order of magnitude, the points of a line from left to right, the moments of time from earlier to later, are instances of series. The notion of order, which is here introduced, is one which is not required in the theory of cardinal number. It is possible to know that two classes have the same number of terms without knowing any order in which they are to be taken. We have an instance of this in such a case as English husbands and English wives. We can see that there must be the same number of husbands as of wives, without having to arrange them in a series. But continuity, which we are now to consider, is essentially a property of an order. It does not belong to a set of terms in themselves, but only to a set in a certain order. A set of terms which can be arranged in one order can always also be arranged in other orders, and a set of terms which can be arranged in a continuous order can always be arranged in orders which are not continuous. Thus, the essence of continuity must not be sought in the nature of the set of terms, but in the nature of their arrangement in a series. Mathematicians have distinguished different degrees of continuity, and have confined the word continuous, for technical purposes, to series having a certain high degree of continuity. But for philosophical purposes, all that is important in continuity is introduced by the lowest degree of continuity, which is called compactness. A series is called compact when no two terms are consecutive, but between any two there are others. One of the simplest examples of a compact series is the series of fractions in order of magnitude. Given any two fractions, however near together, there are other fractions greater than the one and smaller than the other, and therefore no two fractions are consecutive. There is no fraction, for example, which is next after 1/2. If we choose some fraction which is very little greater than 1/2, say 51/100, we can find others, such as 101/200ths, which are nearer to 1/2. Thus, between any two fractions, however little they differ, there are an infinite number of other fractions. Mathematical space and time also have this property of compactness, though whether actual space and time have it is a further question, dependent upon empirical evidence, and probably incapable of being answered with certainty. In the case of abstract objects such as fractions, it is perhaps not very difficult to realize the logical possibility of their forming a compact series. The difficulties that might be felt are those of infinity. For in a compact series, the number of terms between any two given terms must be infinite. But when these difficulties have been solved, the mere compactness in itself offers no great obstacle to the imagination. In more concrete cases, however, such as motion, compactness becomes much more repugnant to our habits of thought. It will, therefore, be desirable to consider explicitly the mathematical account of motion, with a view to making its logical possibility felt. The mathematical account of motion is perhaps artificially simplified when regarded as describing what actually occurs in the physical world, but what actually occurs must be capable, by a certain amount of logical manipulation, of being brought within the scope of the mathematical account, and must, in its analysis, raise just such problems as are raised in their simplest form by this account. Neglecting, therefore, for the present, the question of its physical adequacy, let us devote ourselves merely to considering its possibility as a formal statement of the nature of motion. In order to simplify our problem as much as possible, let us imagine a tiny speck of light moving along a scale. What do we mean by saying that motion is continuous? It is not necessary for our purposes to consider the whole of what the mathematician means by this statement. Only part of what he means is philosophically important. One part of what he means is that if we consider any two positions of the speck occupied at any two instants, there will be other intermediate positions occupied at intermediate instants. However near together we take the two positions, the speck will not jump suddenly from the one to the other, but will pass through an infinite number of other positions on the way. Every distance, however small, is traversed by passing through all the infinite series of positions between the two ends of the space. But at this point, imagination suggests that we may describe the continuity of motion by saying that the speck always passes from one position at one instant to the next position at the next instant. As soon as we say this, or imagine it, we fall into error, because there is no next point or next instant. If there were, we should find Zeno's paradoxes, in some form, unavoidable, as will appear in our next lecture. One simple paradox may serve as an illustration. If our speck is in motion along the scale throughout the whole of a certain time, it cannot be at the same point at two consecutive instants. But it cannot, from one instant to the next, travel further than from one point to the next, for if it did, there would be no instant at which it was in the positions intermediate between that at the first instant and that at the next, and we agree that the continuity of motion excludes the possibility of such sudden jumps. It follows that our speck must, so long as it moves, pass from one point at one instant to the next point at the next instant. Thus, there will be just one perfectly definite velocity with which all motions must take place. No motion can be faster than this, and no motion can be slower. Since this conclusion is false, we must reject the hypothesis upon which it is based, namely, that there are consecutive points and instants. Footnote 1. The above paradox is essentially the same as Zeno's argument of the stadium, which will be considered in our next lecture. End of footnote 1. Hence, the continuity of motion must not be supposed to consist in a body's occupying consecutive positions at consecutive times. The difficulty to imagination lies chiefly, I think, in keeping out the suggestion of infinitesimal distances and times. Suppose we have a given distance, and then have the half, and so on. We can continue the process as long as we please, and the longer we continue it, the smaller the resulting distance becomes. This infinite divisibility seems, at first sight, to imply that there are infinitesimal distances, that is, distances so small that any finite fraction of an inch would be greater. This, however, is an error. The continued bisection of our distances, though it gives us continually smaller distances, gives us always finite distances. If our original distance was an inch, we reach successively half an inch, a quarter of an inch, an eighth, a 16th, and so on. But every one of this infinite series of diminishing distances is finite. But, it may be said, in the end the distance will grow infinitesimal. No, because there is no end. The process of bisection is one which can, theoretically, be carried on forever, without any last term being attained. Thus, infinite divisibility of distances, which must be admitted, does not imply that there are distances so small that any finite distance would be larger. It is easy, in this kind of question, to fall into an elementary logical blunder. Given any finite distance, we can find a smaller distance. This may be expressed in the ambiguous form, there is a distance smaller than any finite distance. But if this is then interpreted as meaning there is a distance such that, whatever finite distance may be chosen, the distance in question is smaller, then the statement is false. Common language is ill-adapted to expressing matters of this kind, and philosophers who have been dependent on it have frequently been misled by it. In a continuous motion, then, we shall say that at any given instant the moving body occupies a certain position, and at other instants it occupies other positions. The interval between any two instants and between any two positions is always finite. But the continuity of motion is shown in the fact that, however near together we take the two positions and the two instants, there are an infinite number of positions still nearer together, which are occupied at instants that are also still nearer together. The moving body never jumps from one position to another, but always passes by a gradual transition through an infinite number of intermediaries. At a given instant, it is where it is, like Zeno's arrow. Footnote 1. See next lecture. End of footnote 1. But we cannot say that it is at rest at the instant, since the instant does not last for a finite time, and there is not a beginning and end of the instant with an interval between them. Rest consists in being in the same position at all the instants throughout a certain finite period, however short. It does not consist simply in a body's being where it is at a given instant. This whole theory, as is obvious, depends upon the nature of compact series, and demands, for its full comprehension, that compact series should have become familiar and easy to the imagination, as well as to deliberate thought. What is required may be expressed in mathematical language by saying that the position of a moving body must be a continuous function of the time. To define accurately what this means, we proceed as follows. Consider a particle which, at the moment t, is at the point P. Choose now any small portion, P1 to P2, of the path of the particle, this portion being one which contains P. We say, then, that if the motion of the particle is continuous at the time t, it must be possible to find two instants, t1 and t2, one earlier than t and one later, such that throughout the whole time from t1 to t2, both included, the particle lies between p1 and p2. And we say that this might still hold, however small we make the portion p1 to p2. When this is the case, we say that the motion is continuous at the time t, and when the motion is continuous at all times, we say that the motion as a whole is continuous. It is obvious that if the particle were to jump suddenly from P to some other point Q, our definition would fail for all intervals P1 to P2 which were too small to include Q. Thus, our definition affords an analysis of the continuity of motion, while admitting points and instants, and denying infinitesimal distances in space or periods in time. Philosophers, mostly in ignorance of the mathematician's analysis, have adopted other and more heroic methods of dealing with the prima facie difficulties of continuous motion. A typical and recent example of philosophic theories of motion is afforded by Bergson, whose views on this subject I have examined elsewhere. Footnote 1. Monist, July 1912, pages 337 to 341. End of footnote 1. Apart from definite arguments, there are certain feelings, rather than reasons, which stand in the way of an acceptance of the mathematical account of motion. To begin with, if a body is moving at all fast, we see its motion just as we see its color. A slow motion, like that of the hour hand of a watch, is only known in the way which mathematicians would lead us to expect, namely, by observing a change of position after a lapse of time. But when we observe the motion of the second hand, we do not merely see first one position and then another, we see something as directly sensible as color. What is this something that we see, and that we call visible motion? Whatever it is not the successive occupation of successive positions. Something beyond the mathematical theory of motion is required to account for it. Opponents of the mathematical theory emphasize this fact. Your theory, they say, may be very logical and might apply admirably to some other world, but in this actual world, actual motions are quite different from what your theory would declare them to be, and require, therefore, some different philosophy from yours for their adequate explanation. The objection thus raised is one which I have no wish to underrate, but I believe it can be fully answered without departing from the methods and the outlook which have led to the mathematical theory of motion. Let us, however, first try to state the objection more fully. If the mathematical theory is adequate, nothing happens when a body moves except that it is in different places at different times. But in this sense, the hour hand and the second hand are equally in motion. Yet in the second hand, there is something perceptible to our senses which is absent in the hour hand. We can see at each moment that the second hand is moving, which is different from seeing it first in one place and then in another. This seems to involve our seeing it simultaneously in a number of different places, although it must also involve our seeing that it is in some of these places earlier than in others. If, for example, I move my hand quickly from left to right, you seem to see the whole movement at once, in spite of the fact that you know it begins at the left and ends at the right. It is this kind of consideration, I think, which leads Bergson and many others to regard a movement as really one indivisible whole, not the series of separate states imagined by the mathematician. To this objection, there are three supplementary answers: physiological, psychological, and logical. We will consider them successively. 1. The physiological answer merely shows that, if the physical world is what the mathematician supposes, its sensible appearance may nevertheless be expected to be what it is. The aim of this answer is thus the modest one of showing that the mathematical account is not impossible as applied to the physical world. It does not even attempt to show that this account is necessary, or that an analogous account applies in psychology. When any nerve is stimulated so as to cause a sensation, the sensation does not cease instantaneously with the cessation of the stimulus, but dies away in a short, finite time. A flash of lightning, brief as it is to our sight, is briefer still as a physical phenomenon. We continue to see it for a few moments after the light waves have ceased to strike the eye. Thus, in the case of a physical motion, if it is sufficiently swift, we shall actually at one instant see the moving body throughout a finite portion of its course, and not only at the exact spot where it is at that instant. Sensations, however, as they die away, grow gradually fainter. Thus, the sensation due to a stimulus, which is recently past, is not exactly like the sensation due to a present stimulus. It follows from this that, when we see a rapid motion, we shall not only see a number of positions of the moving body simultaneously, but we shall see them with different degrees of intensity, the present position most vividly, and the others with diminishing vividness, until sensation fades away into immediate memory. This state of things accounts fully for the perception of motion. A motion is perceived, not merely inferred, when it is sufficiently swift for many positions to be sensible at one time, and the earlier and later parts of one perceived motion are distinguished by the less and greater vividness of these sensations. This answer shows that physiology can account for our perception of motion, but physiology, in speaking of stimulus and sense organs, and a physical motion distinct from the immediate objects of sense, is assuming the truth of physics, and is thus only capable of showing the physical account to be possible, not of showing it to be necessary. This consideration brings us to the psychological answer. 2. The psychological answer to our difficulty about motion is part of a vast theory, not yet worked out, and only capable at present of being vaguely outlined. We considered this theory in the third and fourth lectures. For the present, a mere sketch of its application to our present problem must suffice. The world of physics, which was assumed in the physiological answer, is obviously inferred from what is given in sensation. Yet as soon as we seriously consider what is actually given in sensation, we find it apparently very different from the world of physics. The question is thus forced upon us: is the inference from sense to physics a valid one? I believe the answer to be affirmative, for reasons which I suggested in the third and fourth lectures, but the answer cannot be either short or easy. It consists, broadly speaking, in showing that, although the particles, points, and instants with which physics operates are not themselves given in experience, and are very likely not actually existing things, yet, out of the materials provided in sensation, together with other particulars structurally similar to these materials, it is possible to make logical constructions having the mathematical properties which physics assigns to particles, points, and instants. If this can be done, then all the propositions of physics can be translated, by a sort of dictionary, into propositions about the kinds of objects which are given in sensation. Applying these general considerations to the case of motion, we find that, even within the sphere of immediate sense data, it is necessary, or at any rate more consonant with the facts than any other equally simple view, to distinguish instantaneous states of objects, and to regard such states as forming a compact series. Let us consider a body which is moving swiftly enough for its motion to be perceptible, and long enough for its motion to be not wholly compromised in one sensation. Then, in spite of the fact that we see a finite extent of the motion at one instant, the extent which we see at one instant is different from that which we see at another. Thus we are brought back, after all, to a series of momentary views of the moving body, and this series will be compact, like the former physical series of points. In fact, though the terms of the series seem different, the mathematical character is unchanged, and the whole mathematical theory of motion will apply to it verbatim. When we are considering the actual data of sensation in this connection, it is important to realize that two sense data may be, and must sometimes be, really different, when we cannot perceive any difference between them. An old but conclusive reason for believing this was emphasized by Poincaré. Footnote 1, Le contenu mathématique, Revue de métaphysique et de morale, Volume 1, page 29. End of footnote 1. In all cases of sense data capable of gradual change, we may find one sense datum indistinguishable from another, and that other indistinguishable from a third, while yet the first and third are quite easily distinguishable. Suppose, for example, a person with his eyes shut is holding a weight in his hand, and someone noiselessly adds a small extra weight. If the extra weight is small enough, no difference will be perceived in the sensation. After a time, another small weight may be added, and still no change will be perceived. But if both extra weights had been added at once, it may be that the change would be quite easily perceptible. Or again, take shades of color. It would be easy to find three stuffs of such closely similar shades that no difference could be perceived between the first and second, nor yet between the second and third, while yet the first and third would be distinguishable. In such a case, the second shade cannot be the same as the first, or would be distinguishable from the third, nor the same as the third, or it would be distinguishable from the first. It must, therefore, though indistinguishable from both, be really intermediate between them. Such considerations as the above show that, although we cannot distinguish sense data unless they differ by more than a certain amount, it is perfectly reasonable to suppose that sense data of a given kind, such as weights or colours, really form a compact series. The objections which may be brought from a psychological point of view against the mathematical theory of motion are not, therefore, objections to this theory properly understood, but only to a quite unnecessary assumption of simplicity in the momentary object of sense. Of the immediate object of sense, in the case of a visible motion, we may say that at each instant it is in all the positions which remain sensible at that instant. But this set of positions changes continuously from moment to moment, and is amenable to exactly the same mathematical treatment as if it were a mere point. When we assert that some mathematical account of phenomena is correct, all that we primarily assert is that something definable in terms of the crude phenomena satisfies our formulae. And in this sense, the mathematical theory of motion is applicable to the data of sensation, as well as to the supposed particles of abstract physics. There are a number of distinct questions, which are apt to be confused when the mathematical continuum is said to be inadequate to the facts of sense. We may state, in order of diminishing generality, as follows. A. Are series possessing mathematical continuity logically possible? B. Assuming that they are possible logically, are they not impossible as applied to actual sense data? Because, among actual sense data, there are no such fixed, mutually external terms as are to be found, for example, in the series of fractions. C. Does not the assumption of points and instants make the whole mathematical account fictitious? D. Finally, assuming that all these objections have been answered, is there, in actual empirical fact, any sufficient reason to believe the world of sense continuous? Let us consider these questions in succession. A. The question of the logical possibility of the mathematical continuum turns partly on the elementary misunderstandings we considered at the beginning of the present lecture, partly on the possibility of the mathematical infinite, which will occupy our next two lectures, and partly on the logical form of the answer to the Bergsonian objection, which we stated a few minutes ago. I shall say no more on this topic at present, since it is desirable first to complete the psychological answer. B. The question whether sense data are composed of mutually external units is not one which can be decided by empirical evidence. It is often urged that, as a matter of immediate experience, the sensible flux is devoid of divisions, and is falsified by the dissections of the intellect. Now I have no wish to argue that this view is contrary to immediate experience. I wish only to maintain that it is essentially incapable of being proved by immediate experience. As we saw, there must be among sense data differences so slight as to be imperceptible. The fact that sense data are immediately given does not mean that their differences also must be immediately given, though they may be. Suppose, for example, a colored surface on which the color changes gradually, so gradually that the difference of color in two very neighbouring portions is imperceptible, while the difference between more widely separated portions is quite noticeable. The effect produced in such a case will be precisely that of interpenetration, of transition which is not a matter of discrete units. And since it tends to be supposed that the colours, being immediate data, must appear different if they are different, it seems easily to follow that interpenetration must be the ultimately right account. But this does not follow. It is unconsciously assumed, as a premise for a reductio ad absurdum of the analytic view, that if A and B are immediate data, and A differs from B, then the fact that they differ must also be an immediate datum. It is difficult to say how this assumption arose, but I think it is to be connected with the confusion between acquaintance and knowledge about. Acquaintance, which is what we derive from sense, does not, theoretically at least, imply even the smallest knowledge about. That is, it does not imply knowledge of any proposition concerning the object with which we are acquainted. It is a mistake to speak as if acquaintance had degrees. There is merely acquaintance and non-acquaintance. When we speak of becoming better acquainted, as for instance with a person, what we must mean is becoming acquainted with more parts of a certain whole. But the acquaintance with each part is either complete or non-existent. Thus it is a mistake to say that if we were perfectly acquainted with an object, we should know all about it. Knowledge about is knowledge of propositions, which is not involved necessarily in acquaintance with the constituents of the propositions. To know that two shades of color are different is knowledge about them. Hence, acquaintance with the two shades does not in any way necessitate the knowledge that they are different. From what has just been said, it follows that the nature of sense data cannot be validly used to prove that they are not composed of mutually external units. It may be admitted, on the other hand, that nothing in their empirical character specially necessitates the view that they are composed of mutually external units. This view, if it is held, must be held on logical, not on empirical, grounds. I believe that the logical grounds are adequate to the conclusion. They rest, at bottom, upon the impossibility of explaining complexity without assuming constituents. It is undeniable that the visual field, for example, is complex, and so far as I can see, there is always self-contradiction in the theories which, while admitting this complexity, attempt to deny that it results from a combination of mutually external units. But to pursue this topic would lead us too far from our theme, and I shall therefore say no more about it at present. C. It is sometimes urged that the mathematical account of motion is rendered fictitious by its assumption of points and instants. Now there are here two different questions to be distinguished. There is the question of absolute or relative space and time, and there is the question whether what occupies space and time must be composed of elements which have no extension or duration. And each of these questions, in turn, may take two forms, namely, alpha, is the hypothesis consistent with the facts and with logic? Beta, is it necessitated by the facts or by logic? I wish to answer, in each case, yes to the first form of the question, and no to the second. But in any case, the mathematical account of motion will not be fictitious, provided a right interpretation is given to the words point and instant. A few words on each alternative will serve to make this clear. Formally, mathematics adopts an absolute theory of space and time. That is, it assumes that, besides the things which are in space and time, there are also entities called points and instants, which are occupied by things. This view, however, though advocated by Newton, has long been regarded by mathematicians as merely a convenient fiction. There is, so far as I can see, no conceivable evidence either for or against it. It is logically possible, and it is consistent with the facts, but the facts are also consistent with the denial of spatial and temporal entities over and above things with spatial and temporal relations. Hence, in accordance with Occam's razor, we shall do well to abstain from either assuming or denying points and instants. This means, so far as practical working out is concerned, that we adopt the relational theory. For in practice, the refusal to assume points and instants has the same effect as the denial of them. But in strict theory, the two are quite different, since the denial introduces an element of unverifiable dogma, which is wholly absent when we merely refrain from the assertion. Thus, although we shall derive points and instants from things, we shall leave the bare possibility open that they may also have an independent existence as simple entities. We come now to the question whether the things in space and time are to be conceived as composed of elements without extension or duration, that is, of elements which only occupy a point and an instant. Physics formally assumes in its differential equations that things consist of elements which occupy only a point at each instant, but persist throughout time. For reasons explained in Lecture 4, the persistence of things through time is to be regarded as the formal result of a logical construction, not as necessarily implying any actual persistence. The same motives, in fact, which lead to the division of things into point particles ought presumably to lead to their division into instant particles, so that the ultimate formal constituent of the matter in physics will be a point instant particle. But such objects, as well as the particles of physics, are not data. The same economy of hypothesis, which dictates the practical adoption of a relative rather than an absolute space and time, also dictates the practical adoption of material elements which have a finite extension and duration. Since, as we saw in Lecture 4, points and instants can be constructed as logical functions of such elements, the mathematical account of motion, in which a particle passes continuously through a continuous series of points, can be interpreted in a form which assumes only elements which agree with our actual data in having a finite extension and duration. Thus, so far as the use of points and instants is concerned, the mathematical account of motion can be freed from the charge of employing fictions. D. But we must now face the question, is there an actual empirical fact any sufficient reason to believe the world of sense continuous? The answer here must, I think, be in the negative. We may say that the hypothesis of continuity is perfectly consistent with the facts and with logic, and that it is technically simpler than any other tenable hypothesis. But since our powers of discrimination among very similar sensible objects are not infinitely precise, it is quite impossible to decide between different theories which only differ in regard to what is below the margin of discrimination. If, for example, a coloured surface which we see consists of a finite number of very small surfaces, and if a motion which we see consists, like a cinematograph, of a large finite number of successive positions, there will be nothing empirically discoverable to show that objects of sense are not continuous. In what is called experienced continuity, such as is said to be given in sense, there is a large negative element. Absence of perception of difference occurs in cases which are thought to give perception of absence of difference. When, for example, we cannot distinguish a colour A from a colour B, nor a colour B from a colour C, but can distinguish A from C, the indistinguishability is a purely negative fact, namely, that we do not perceive a difference. Even in regard to immediate data, there is no reason for denying that there is a difference. Thus, if we see a coloured surface whose colour changes gradually, its sensible appearance, if the change is continuous, will be indistinguishable from what it would be if the change were by small, finite jumps. If this is true, as it seems to be, it follows that there can never be any empirical evidence to demonstrate that the sensible world is continuous, and not a collection of a very large finite number of elements, of which each differs from its neighbour in a finite, though very small, degree. The continuity of space and time, the infinite number of different shades in the spectrum, and so on, are all in the nature of unverifiable hypotheses, perfectly possible logically, perfectly consistent with the known facts, and simpler technically than any other tenable hypotheses, but not the sole hypotheses which are logically and empirically adequate. If a relational theory of instants is constructed, in which an instant is defined as a group of events simultaneous with each other and not all simultaneous with any event outside the group, then if our resulting series of instants is to be compact, it must be possible, if x wholly precedes y, to find an event z simultaneous with part of x which wholly precedes some event which wholly precedes y. Now this requires that the number of events concerned should be infinite in any finite period of time. If this is to be the case in the world of one man's sense data, and if each sense datum is to have not less than a certain finite temporal extension, it will be necessary to assume that we always have an infinite number of sense data, simultaneous with any given sense datum. Applying similar considerations to space, and assuming that sense data are to have not less than a certain spatial extension, it will be necessary to suppose that an infinite number of sense data overlap spatially with any given sense datum. This hypothesis is possible if we suppose a single sense datum, for example in sight, to be a finite surface, enclosing other surfaces which are also single sense data. But there are difficulties in such a hypothesis, and I do not think that these difficulties could be successfully met. If they cannot, we must do one of two things: either declare that the world of one man's sense data is not continuous, or else refuse to admit that there is any lower limit to the duration and extension of a single sense datum. The latter hypothesis seems untenable, so that we are apparently forced to conclude that the space of sense data is not continuous. But that does not prevent us from admitting that sense data have parts which are not sense data, and that the space of these parts may be continuous. The logical analysis we have been considering provides the apparatus for dealing with the various hypotheses, and the empirical decision between them is a problem for the psychologist. 3. We have now to consider the logical answer to the alleged difficulties of the mathematical theory of motion, or rather to the positive theory which is urged on the other side. The view urged explicitly by Bergson and implied in the doctrines of many philosophers is that a motion is something indivisible, not validly analysable into a series of states. This is part of a much more general doctrine, which holds that analysis always falsifies, because the parts of a complex whole are different, as combined in that whole, from what they would otherwise be. It is very difficult to state this doctrine in any form which has a precise meaning. Often arguments are used which have no bearing whatever upon the question. It is urged, for example, that when a man becomes a father, his nature is altered by the new relation in which he finds himself, so that he is not strictly identical with the man who was previously not a father. This may be true, but it is a causal psychological fact, not a logical fact. The doctrine would require that a man who is a father cannot be strictly identical with a man who is a son, because he is modified in one way by the relation of fatherhood and in another by that of sonship. In fact, we may give a precise statement of the doctrine we are combating in the form, "There can never be two facts concerning the same thing." A fact concerning a thing always is or involves a relation to one or more entities. Thus, two facts concerning the same thing would involve two relations of the same thing. But the doctrine in question holds that a thing is so modified by its relations that it cannot be the same in one relation as in another. Hence, if this doctrine is true, there can never be more than one fact concerning any one thing. I do not think the philosophers in question have realized that this is the precise statement of the view they advocate, because in this form the view is so contrary to plain truth that its falsehood is evident as soon as it is stated. The discussion of this question, however, involves so many logical subtleties and is so beset with difficulties that I shall not pursue it further at present. When once the above general doctrine is rejected, it is obvious that, where there is change, there must be a succession of states. There cannot be change, and motion is only a particular case of change, unless there is something different at one time from what there is at some other time. Change, therefore, must involve relations and complexity, and must demand analysis. So long as our analysis has only gone as far as other smaller changes, it is not complete. If it is to be complete, it must end with terms that are not changes, but are related by a relation of earlier and later. In the case of changes which appear continuous, such as motions, it seems to be impossible to find anything other than change so long as we deal with finite periods of time, however short. We are thus driven back, by the logical necessities of the case, to the conception of instants without duration, or at any rate, without duration which even the most delicate instruments can reveal. This conception, though it can be made to seem difficult, is really easier than any other that the facts allow. It is a kind of logical framework into which any tenable theory must fit, not necessarily itself the statement of the crude facts, but a form in which statements which are true of the crude facts can be made by a suitable interpretation. The direct consideration of the crude facts of the physical world has been undertaken in earlier lectures. In the present lecture, we have only been concerned to show that nothing in the crude facts is inconsistent with the mathematical doctrine of continuity, or demands a continuity of a radically different kind from that of mathematical motion. End of Lecture 5. Lecture 6 of Our Knowledge of the External World as a Field for Scientific Method in Philosophy by Bertrand Russell. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Landon D. Elkind at the University of Iowa in Iowa City, Iowa. The problem of infinity considered historically. It will be remembered that, when we enumerated the grounds upon which the reality of the sensible world has been questioned, one of those mentioned was the supposed impossibility of infinity and continuity. In view of our earlier discussion of physics, it would seem that no conclusive empirical evidence exists in favour of infinity or continuity in objects of sense or in matter. Nevertheless, the explanation which assumes infinity and continuity remains incomparably easier and more natural, from a scientific point of view, than any other. And since Georg Cantor has shown that the supposed contradictions are illusory, there is no longer any reason to struggle after a finitist explanation of the world. The supposed difficulties of continuity all have their source in the fact that a continuous series must have an infinite number of terms, and are in fact difficulties concerning infinity. Hence, in freeing the infinite from contradiction, we are at the same time showing the logical possibility of continuity, as assumed in science. The kind of way in which infinity has been used to discredit the world of sense may be illustrated by Kant's first two antinomies. In the first, the thesis states, the world has a beginning in time, and as regards space is enclosed within limits. The antithesis states, the world has no beginning and no limits in space, but is infinite in respect of both time and space. Kant professes to prove both these propositions, whereas if what we have said on modern logic has any truth, it must be impossible to prove either. In order, however, to rescue the world of sense, it is enough to destroy the proof of one of the two. For our present purpose, it is the proof that the world is finite that interests us. Kant's argument as regards space here rests upon his argument as regards time. We need therefore only examine the argument as regards time. What he says is as follows. For let us assume that the world has no beginning as regards time, so that up to every given instant an eternity has elapsed, and therefore an infinite series of successive states of the things in the world has passed by. But the infinity of a series consists just in this, that it can never be completed by successive synthesis. Therefore an infinite past world series is impossible, and accordingly a beginning of the world is a necessary condition of its existence, which was the first thing to be proved. Many different criticisms might be passed on this argument, but we will content ourselves with a bare minimum. To begin with, it is a mistake to define the infinity of a series as impossibility of completion by successive synthesis. The notion of infinity, as we shall see in the next lecture, is primarily a property of classes, and only derivatively applicable to series. Classes which are infinite are given all at once by the defining property of their members, so that there is no question of completion or of successive synthesis. And the word synthesis, by suggesting the mental activity of synthesizing, introduces, more or less surreptitiously, that reference to mind by which all Kant's philosophy was infected. In the second place, when Kant says that an infinite series can never be completed by successive synthesis, all that he has even conceivably a right to say is that it cannot be completed in a finite time. Thus, what he really proves is, at most, that if the world had no beginning, it must have already existed for an infinite time. This, however, is a very poor conclusion, by no means suitable for his purposes. And with this result, we might, if we chose, take leave of the first antinomy. It is worthwhile, however, to consider how Kant came to such an elementary blunder. What happened in his imagination was obviously something like this. Starting from the present and going backwards in time, we have, if the world had no beginning, an infinite series of events. As we see from the word synthesis, he imagined a mind trying to grasp these successively, in the reverse order to that in which they had occurred, that is, going from the present backwards. This series is obviously one which has no end, but the series of events up to the present has an end, since it ends with the present. Owing to the inveterate subjectivism of his mental habits, he failed to notice that he had reversed the sense of the series by substituting backward synthesis for forward happening, and thus he supposed that it was necessary to identify the mental series, which had no end, with the physical series, which had an end but no beginning. It was this mistake, I think, which, operating unconsciously, led him to attribute validity to a singular flimsy piece of fallacious reasoning. The second antinomy illustrates the dependence of the problem of continuity upon that of infinity. The thesis states, "Every complex substance in the world consists of simple parts, and there exists, everywhere, nothing but the simple, or what is composed of it." The antithesis states, "No complex thing in the world consists of simple parts, and everywhere in it there exists nothing simple." Here, as before, the proofs of both thesis and antithesis are open to criticism. But for the purpose of vindicating physics and the world of sense, it is enough to find a fallacy in one of the proofs. We will choose for this purpose the proof of the antithesis, which begins as follows. Assume that a complex thing as substance consists of simple parts, since all external relation, and therefore all composition out of substances, is only possible in space. The space occupied by a complex thing must consist of as many parts as the thing consists of. Now, space does not consist of simple parts, but of spaces. The rest of his argument need not concern us, for the nerve of the proof lies in the one statement: space does not consist of simple parts, but of spaces. This is like Bergson's objection to the absurd proposition that motion is made up of immobilities. Kant does not tell us why he holds that a space must consist of spaces rather than of simple parts. Geometry regards space as made up of points, which are simple, and although, as we have seen, this view is not scientifically or logically necessary, it remains prima facie possible, and its mere possibility is enough to vitiate Kant's argument. For if his proof of the thesis of the antinomy were valid, and if the antithesis could only be avoided by assuming points, then the antinomy itself would afford a conclusive reason in favour of points. Why, then, did Kant think it impossible that space should be composed of points? I think two considerations probably influenced him. In the first place, the essential thing about space is spatial order, and mere points by themselves will not account for spatial order. It is obvious that his argument assumes absolute space, but it is spatial relations that are alone important, and they cannot be reduced to points. This ground for his view depends, therefore, upon his ignorance of the logical theory of order, and his oscillations between absolute and relative space. But there is also another ground for his opinion, which is more relevant to our present topic. This is the ground derived from infinite divisibility. A space may be halved, and then halved again, and so on ad infinitum. And at every stage of the process, the parts are still spaces, not points. In order to reach the points by such a method, it would be necessary to come to the end of an unending process, which is impossible. But just as an infinite class can be given all at once by its defining concept, though it cannot be reached by successive enumeration, so an infinite set of points can be given all at once, as making up a line or area or volume, though they can never be reached by the process of successive division. Thus, the infinite divisibility of space gives no ground for denying that space is composed of points. Kant does not give his grounds for this denial, and we can therefore only conjecture what they were. But the above two grounds, which we have seen to be fallacious, seem sufficient to account for his opinion, and we may therefore conclude that the antithesis of the second antinomy is unproved. The above illustration of Kant's antinomies has only been introduced in order to show the relevance of the problem of infinity to the problem of the reality of objects of sense. In the remainder of the present lecture, I wish to state and explain the problem of infinity, to show how it arose, and to show the irrelevance of all the solutions proposed by philosophers. In the following lecture, I shall try to explain the true solution, which has been discovered by the mathematicians, but nevertheless belongs essentially to philosophy. The solution is definitive, in the sense that it entirely satisfies and convinces all who study it carefully. For over 2,000 years, the human intellect was baffled by the problem. Its many failures and its ultimate success make this problem peculiarly apt for the illustration of method. The problem appears to have first arisen in some such way as the following. Footnote 1. In what concerns the early Greek philosophers, my knowledge is largely derived from Burnet's valuable work, Early Greek Philosophy, 2nd edition, London, 1908. I have also been greatly assisted by Mr. D. S. Robertson of Trinity College, who has supplied the deficiencies of my knowledge of Greek and brought important references to my notice. End of footnote 1. Pythagoras and his followers, who were interested, like Descartes, in the application of number to geometry, adopted in that science more arithmetical methods than those with which Euclid has made us familiar. They, or their contemporaries the atomists, believed, apparently, that space is composed of indivisible points, while time is composed of indivisible instants. Footnote 2. Confer Aristotle, Metaphysics M6, 1080b, 18 and the following, and 1083b, 8 and the following. End of footnote 2. This belief would not, by itself, have raised the difficulties which they encountered, but it was presumably accompanied by another belief, that the number of points in any finite area or of instants in any finite period must be finite. I do not suppose that this latter belief was a conscious one, because probably no other possibility had occurred to them. But the belief nevertheless operated, and very soon brought them into conflict with facts which they themselves discovered. Before explaining how this occurred, however, it is necessary to say one word in explanation of the phrase finite number. The exact explanation is a matter for our next lecture. For the present, it must suffice to say that I mean 0 and 1 and 2 and 3 and so on, forever. In other words, any number that can be obtained by successively adding ones. This includes all the numbers that can be expressed by means of our ordinary numerals, and since such numbers can be made greater and greater without ever reaching an unsurpassable maximum, it is easy to suppose that there are no other numbers. But this supposition, natural as it is mistaken. Whether the Pythagoreans themselves believed space and time to be composed of indivisible points and instants is a debatable question. Footnote 1. There is some reason to think that the Pythagoreans distinguished between discrete and continuous quantity. G. J. Allman, in his Greek Geometry from Thales to Euclid, says, page 23, "The Pythagoreans made a fourfold division of mathematical science, attributing one of its parts to the how many, to poson, and the other to the how much, to pelikon, and they assigned to each of those parts a twofold division. For they said that discrete quantity, or the how many, either subsists by itself or must be considered with relation to some other, but that continued quantity, or the how much, is either stable or in motion. Hence they affirmed that arithmetic contemplates that discrete quantity which subsists by itself, but music that which is related to another, and that geometry considers continued quantity so far as it is immovable, but astronomy, ten Sephairiken, contemplates continued quantity so far as it is of a self-motive nature." Proclus, edited by Friedlein, page 35. As to the distinction between to pelikon, continuous, and to poson, discrete quantity, see Iamblichus in Nicomachi Geraseni Arithmeticam Introductionem, edited by Tenulius, page 148. Confer page 48. End of footnote 1. It would seem that the distinction between space and matter had not yet been clearly made, and that, therefore, when an atomistic view is expressed, it is difficult to decide whether particles of matter or points of space are intended. There is an interesting passage, footnote 1, referred to by Burnet, open citation, page 120, end of footnote 1. In Aristotle's Physics, footnote 2, Book 4, Chapter 6, 213b, 22. H. Ritter and L. Preller, Historia Philosophiae Grisae, 8th edition, Gotha, 1898, page 75. This work will be referred to in future as RP. End of footnote 2. Where he says, "The Pythagoreans all maintain the existence of the void, and said that it enters into the heaven itself from the boundless breath, inasmuch as the heaven breathes in the void also, and the void differentiates natures, as if it were a sort of separation of consecutives, and as if it were their differentiation, and that this also is what is first in numbers, for it is the void which differentiates them." This seems to imply that they regarded matter as consisting of atoms with empty space in between. But if so, they must have thought space could be studied only by paying attention to the atoms, for otherwise it would be very hard to account for their arithmetical methods in geometry, or for their statement that things are numbers. The difficulty which beset the Pythagoreans in their attempts to apply numbers arose through their discovery of incommensurables, and this in turn arose as follows. Pythagoras, as we all learnt in youth, discovered the proposition that the sum of the squares on the sides of a right-angled triangle is equal to the square on the hypotenuse. It is said that he sacrificed an ox when he discovered this theorem. If so, the ox was the first martyr to science. But the theorem, though it has remained his chief claim to immortality, was soon found to have a consequence fatal to his whole philosophy. Consider the case of a right-angled triangle whose two sides are equal, such a triangle as is formed by two sides of a square and a diagonal. Here, in virtue of the theorem, the square on the diagonal is double of the square on either of the sides. But Pythagoras, or his early followers, easily proved that the square of one whole number cannot be double of the square of another. Footnote 1. The Pythagorean proof is roughly as follows. If possible, let the ratio of the diagonal to the side of a square be m over n, where m and n are whole numbers, having no common factor. Then we must have m squared is equal to 2n squared. Now the square of an odd number is odd, but m squared being equal to 2n squared is even. Hence m must be even. But the square of an even number divides 4. Therefore n squared, which is half of m squared, must be even. Therefore, n must be even. But since m is even, and m and n have no common factor, n must be odd. Thus, n must be both odd and even, which is impossible, and therefore the diagonal and the side cannot have a rational ratio. End of footnote 1. Thus, the length of the side and the length of the diagonal are incommensurable. That is to say, however small a unit of length you take, if it is contained an exact number of times in the side, it is not contained any exact number of times in the diagonal, and vice versa. Now this fact might have been assimilated by some philosophies without any great difficulty, but to the philosophy of Pythagoras it was absolutely fatal. Pythagoras held that number is the constitutive essence of all things, yet no two numbers could express the ratio of the side of a square to the diagonal. It would seem probable that we may expand his difficulty without departing from his thought by assuming that he regarded the length of the line as determined by the number of atoms contained in it. A line 2 inches long would contain twice as many atoms as a line 1 inch long, and so on. But if this were the truth, then there must be a definite numerical ratio between any two finite lengths, because it was supposed that the number of atoms in each, however large, must be finite. Here there was an insoluble contradiction. The Pythagoreans, it is said, resolved to keep the existence of incommensurables a profound secret, revealed only to a few of the supreme heads of the sect, and one of their number, Hippasos of Metapontion, is even said to have been shipwrecked at sea for impiously disclosing the terrible discovery to their enemies. It must be remembered that Pythagoras was the founder of a new religion as well as the teacher of a new science. If the science came to be doubted, the disciples might fall into sin, and perhaps even eat beans, which according to Pythagoras is as bad as eating parents' bones. The problem first raised by the discovery of incommensurables proved, as time went on, to be one of the most severe and at the same time most far-reaching problems that have confronted the human intellect in its endeavour to understand the world. It showed at once that numerical measurement of lengths, if it was to be made accurate, must require an arithmetic more advanced and more difficult than any that the ancients possessed. They therefore set to work to reconstruct geometry on a basis which did not assume the universal possibility of numerical measurement, a reconstruction which, as may be seen in Euclid, they effected with extraordinary skill and with great logical acumen. The moderns, under the influence of Cartesian geometry, have reasserted the universal possibility of numerical measurement, extending arithmetic, partly for that purpose, so as to include what are called irrational numbers, which give the ratios of incommensurable lengths. But although irrational numbers have long been used without a qualm, it is only in quite recent years that logically satisfactory definitions of them have been given. With these definitions, the first and most obvious form of the difficulty which confronted the Pythagoreans has been solved, but other forms of the difficulty remain to be considered, and it is these that introduce us to the problem of infinity in its pure form. We saw that, accepting the view that a length is composed of points, the existence of incommensurables proves that every finite length must contain an infinite number of points. In other words, if we were to take away points one by one, we should never have taken away all those points, however long we continued the process. The number of points, therefore, cannot be counted, for counting is a process which enumerates things one by one. The property of being unable to be counted is characteristic of infinite collections, and is a source of many of their paradoxical qualities. So paradoxical are these qualities that until our own day they were thought to constitute logical contradictions. A long line of philosophers, from Zeno, footnote 1, in regard to Zeno and the Pythagoreans, I have derived much valuable information and criticism from Mr. P. E. B. Jourdain, end of footnote 1, to M. Bergson, have based much of their metaphysics upon the supposed impossibility of infinite collections. Broadly speaking, the difficulties were stated by Zeno, and nothing material was added until we reach Bolzano's Paradoxien des Unendlichen, a little work written in 1847 to 1848 and published posthumously in 1851. Intervening attempts to deal with the problem are futile and negligible. The definitive solution of these difficulties is due not to Bolzano, but to Georg Cantor, whose work on this subject first appeared in 1882. In order to understand Zeno, and to realize how little modern orthodox metaphysics has added to the achievements of the Greeks, we must consider for a moment his master, Parmenides, in whose interests the paradoxes were invented. Footnote 1. So Plato makes Zeno say in the Parmenides, apropos of his philosophy as a whole, and all internal and external evidence supports this view. End of footnote 1. Parmenides expounded his views in a poem divided into two parts, called The Way of Truth and The Way of Opinion, like Mr. Bradley's Appearance and Reality, except that Parmenides tells us first about reality and then about appearance. The Way of Opinion in his philosophy is, broadly speaking, Pythagoreanism. It begins with a warning. Here I shall close my trustworthy speech and thought about the truth. Henceforward learn the opinions of mortals, giving ear to the deceptive ordering of my words. What has gone before has been revealed by a goddess, who tells him what really is. Reality, she says, is uncreated, indestructible, unchanging, indivisible. It is immovable in the bonds of mighty chains, without beginning and without end, since coming into being and passing away have been driven afar, and true belief has cast them away. The fundamental principle of his inquiry is stated in a sentence which would not be out of place in Hegel. Footnote 2. With Parmenides, Hegel says, philosophizing proper began. Furka, edition of 1840, volume 13, page 274. End of footnote 2. Thou canst not know what is not, that is impossible, nor utter it, for it is the same thing that can be thought, and that can be. And again, it needs must be that what can be thought and spoken of is, for it is possible for it to be, and it is not possible for what is nothing to be. The impossibility of change follows from this principle, for what is past can be spoken of, and therefore, by the principle, still is. The great conception of a reality behind the passing illusions of sense, a reality one, indivisible, and unchanging, was thus introduced into Western philosophy by Parmenides. Not, it would seem, for mystical or religious reasons, but on the basis of a logical argument as to the impossibility of not being. All the great metaphysical systems, notably those of Plato, Spinoza, and Hegel, are the outcome of this fundamental idea. It is difficult to disentangle the truth and the error in this view. The contention that time is unreal, and that the world of sense is illusory, must, I think, be regarded as based upon fallacious reasoning. Nevertheless, there is some sense, easier to feel than to state, in which time is an unimportant and superficial characteristic of reality. Past and future must be acknowledged to be as real as the present, and a certain emancipation from slavery to time is essential to philosophic thought. The importance of time is rather practical than theoretical, rather in relation to our desires than in relation to truth. A truer image of the world, I think, is obtained by picturing things as entering into the stream of time from an eternal world outside, than from a view which regards time as the devouring tyrant of all that is. Both in thought and in feeling, to realize the unimportance of time is the gate of wisdom. But unimportance is not unreality. And therefore what we shall have to say about Zeno's arguments in support of Parmenides must be mainly critical. The relation of Zeno to Parmenides is explained by Plato. Footnote 1. Parmenides 128a through d. End of footnote 1. in the dialogue in which Socrates, as a young man, learns logical acumen and philosophic disinterestedness from their dialectic. I quote from Jowett's translation. "I see, Parmenides," said Socrates, "that Zeno is your second self in his writings too. He puts what you say in another way, and would fain deceive us into believing that he is telling us what is new. For you in your poems say all is one, and of this you adduce excellent proofs. And he, on the other hand, says there is no many, and on behalf of this he offers overwhelming evidence. To deceive the world as you have done, by saying the same thing in different ways, one of you affirming the one, and the other denying the many, is a strain of art beyond the reach of most of us." "Yes, Socrates," said Zeno, "but although you are as keen as a Spartan hound in pursuing the track, you do not quite apprehend the true motive of the composition, which is not really such an ambitious work as you imagine. For what you speak of was an accident. I had no serious intention of deceiving the world. The truth is that these writings of mine were meant to protect the arguments of Parmenides against those who scoff at him and show the many ridiculous and contradictory results which they suppose to follow from the affirmation of the one. My answer is an address to the partisans of the many, whose attack I return with interest by retorting upon them that their hypothesis of the being of the many, if carried out, appears in a still more ridiculous light than the hypothesis of the being of the one." Zeno's four arguments against motion were intended to exhibit the contradictions that result from supposing that there is such a thing as change, and thus to support the Parmenidean doctrine that reality is unchanging. Footnote 1. This interpretation is combated by Milhaud, La philosophie géométrie de la Grèce, page 140, note, but his reasons do not seem to me convincing. All the interpretations in what follows are open to question, but all have the support of reputable authorities. End of footnote 1. Unfortunately, we only know his arguments through Aristotle. Footnote 1. Physics, Book 6, Chapter 9, 2396. RP 136-139. End of footnote 1. Who stated them in order to refute them. Those philosophers in the present day who have had their doctrines stated by opponents will realize that a just or adequate presentation of Zeno's position is hardly to be expected from Aristotle. But by some care in interpretation, it seems possible to reconstruct the so-called sophisms which have been refuted by every tyro from that day to this. Zeno's arguments would seem to be ad hominem, that is to say, they seem to assume premises granted by his opponents, and to show that, granting these premises, it is possible to deduce consequences which his opponents must deny. In order to decide whether they are valid arguments or sophisms, it is necessary to guess at the tacit premises, and to decide who was the homo at which they were aimed. Some maintain that they were aimed at the Pythagoreans. Footnote 2. Confer Gaston Milhaud, Les philosophies géométriques de la Grèce, page 140, note. Paul Tannery, Pour l'histoire de la science Aline, page 249, Burnett, open citation, page 362. End of footnote 2. While others have held that they were intended to refute the atomists. Footnote 3. Confer R.K. Gay on Aristotle Physics Zeta 4, Journal of Philology, volume 31, especially page 111. Also Moritz Cantor, Vorlesungen über Geschichte der Mathematik, first edition, volume 1, 1880, page 161, who, however, subsequently adopted Paul Tannery's opinion, Vorlesungen, third edition, volume 1, page 200. End of footnote 3. M. Evelyn, on the contrary, holds that they constitute a refutation of infinite divisibility. Footnote 4. Le mouvement et les partisans des invisibles. Revue de métaphysique et de morale, volume 1, pages 382 to 395. End of footnote 4. while M.G. Noel, in the interests of Hegel, maintains that the first two arguments refute infinite divisibility, while the next two refute indivisibles. Footnote 1. Le mouvement et les arguments des Zénon de Elie, Revue de métaphysique et de morale, Volume 1, pages 107 to 125. End of footnote 1. Amid such a bewildering variety of interpretations, we can at least not complain of any restrictions on our liberty of choice. The historical questions raised by the above-mentioned discussions are no doubt largely insoluble, owing to the very scanty material from which our evidence is derived. The points which seem fairly clear are the following. 1. That, in spite of M.M. Milhaud and Paul Tannery, Zeno is anxious to prove that motion is really impossible, and that he desires to prove this because he follows Parmenides in denying plurality. Footnote 2. Confer M. Brochard, Les prétendus sophismes de Zénon de Elie, Revue de métaphysique et de morale, Volume 1, pages 209 to 215. End of footnote 2. 2. That the third and fourth arguments proceed on the hypothesis of indivisibles, a hypothesis which, whether adopted by the Pythagoreans or not, was certainly much advocated, as may be seen from the treatise on indivisible lines attributed to Aristotle. As regards the first two arguments, they would seem to be valid on the hypothesis of indivisibles, and also, without this hypothesis, to be such as would be valid if the traditional contradictions in infinite numbers were insoluble, which they are not. We may conclude, therefore, that Zeno's polemic is directed against the view that space and time consist of points and instants, and that, as against the view that a finite stretch of space of time consists of points and instants, his arguments are not sophisms, but perfectly valid. The conclusion which Zeno wishes to draw is that plurality is a delusion, and spaces and times are really indivisible. The other conclusion which is possible, namely that the number of points and instants is infinite, was not tenable so long as the infinite was infected with contradictions. In a fragment which is not one of the four famous arguments against motion, Zeno says, "If things are a many, they must be just as many as they are, and neither more nor less. Now if they are as many as they are, they will be finite in number. If things are a many, they will be infinite in number. For there will always be other things between them, and others again between these, and so things are infinite in number." Footnote 1. Simplicius, Physics, 140, 28d, RP, page 133. Burnett, Open Citation, pages 364 to 365. This argument attempts to prove that if there are many things, the number of them must be both finite and infinite, which is impossible. Hence we are to conclude that there is only one thing. But the weak point in the argument is the phrase, "If they are just as many as they are, they will be finite in number." This phrase is not very clear, but it is plain that it assumes the impossibility of definite infinite numbers. Without this assumption, which is now known to be false, the arguments of Zeno, though they suffice, on certain very reasonable assumptions, to dispel the hypothesis of finite indivisibles, do not suffice to prove that motion and change and plurality are impossible. They are not, however, on any view, mere foolish quibbles. They are serious arguments, raising difficulties which it has taken 2,000 years to answer, and which even now are fatal to the teachings of most philosophers. The first of Zeno's arguments is the argument of the racecourse, which is paraphrased by Burnett as follows. Footnote 1, Open Citation, page 367. End of footnote 1. You cannot get to the end of a racecourse. You cannot traverse an infinite number of points in a finite time. You must traverse the half of any given distance before you traverse the whole, and the half of that again before you can traverse it. This goes on ad infinitum, so that there are an infinite number of points in any given space, and you cannot touch an infinite number one by one in a finite time. Footnote 2. Aristotle's words are, "The first is the one on the non-existence of motion, on the ground that what is moved must always attain the middle point sooner than the end point, on which we gave our opinion in the earlier part of our discourse." Physics, Book 6, Chapter 9, 939b, RP, page 136. Aristotle seems to refer to Physics, Book 6, Chapter 2, 223a through b, RP 136a. All space is continuous, for time and space are divided into the same and equal divisions. Wherefore also Zeno's argument is fallacious, that it is impossible to go through an infinite collection or to touch an infinite collection one by one in a finite time. For there are two senses in which the term infinite is applied, both to length and to time, and in fact to all continuous things, either in regard to divisibility or in regard to the ends. Now it is not possible to touch things infinite in regard to number in a finite time, but it is possible to touch things infinite in regard to divisibility, for time itself also is infinite in this sense, so that in fact we go through an infinite space in an infinite time, and not in a finite time, and we touch infinite things with infinite things, not with finite things. Philoponus, a 6th century commentator, RP 136a, excerpts from Paris Philoponus in Aristotle's Physics, 803 to Vita, gives the following illustration. For if a thing were moved the space of a cubit in 1 hour, since in every space there are an infinite number of points, the thing moved must needs touch all the points of the space. It will then go through an infinite collection in a finite time, which is impossible. End of footnote 2. Zeno appeals here, in the first place, to the fact that any distance, however small, can be halved. From this it follows, of course, that there must be an infinite number of points in a line. But Aristotle represents him as arguing you cannot touch an infinite number of points one by one in a finite time. The words one by one are important. 1. If all the points touched are concerned, then, though you pass them through continuously, you do not touch them one by one. That is to say, after touching one, there is not another which you touch next. No two points are next each other, but between any two, there are always an infinite number of others, which cannot be enumerated one by one. 2. If, on the other hand, only the successive middle points are concerned, obtained by always halving what remains of the course, then the points are reached one by one, and though they are infinite in number, they are in fact all reached in a finite time. His argument to the contrary may be supposed to appeal to the view that a finite time must consist of a finite number of instants, in which case what he says would be perfectly true, on the assumption that the possibility of continued dichotomy is undeniable. If, on the other hand, we suppose the argument directed against the partisans of infinite divisibility, we must suppose it to proceed as follows. Footnote 1. Confer Mr. C.D. Broad, Note on Achilles and the Tortoise, Mind, N.S., Volume 22, pages 318 to 319. End of footnote 1. The points given by successive halving of the distances still to be traversed are infinite in number, and are reached in succession, each being reached a finite time later than its predecessor. But the sum of an infinite number of finite times must be infinite, and therefore the process will never be completed. It is very possible that this is historically the right interpretation, but in this form the argument is invalid. If half the course takes half a minute, the next quarter takes a quarter of a minute, and so on, the whole course will take a minute. The apparent force of the argument on this interpretation lies solely in the mistaken supposition that there cannot be anything between the whole of an infinite series, which can be seen to be false by observing that 1 is beyond the whole of the infinite series, 1/2, 3/4, 7/8, 15/16, and so on. The second of Zeno's arguments is the one concerning Achilles and the tortoise. which has achieved more notoriety than the others. It is paraphrased by Burnet as follows. Footnote 1. Open citation. End of footnote 1. Achilles will never overtake the tortoise. He must first reach the place from which the tortoise started. By that time, the tortoise will have got some way ahead. Achilles must then make up that, and again the tortoise will be ahead. He is always coming nearer, but he never makes up to it. Footnote 2. Aristotle's words are, "The second is the so-called Achilles. It consists in this, that the slower will never be overtaken in its course by the quickest, for the pursuer must always come first to the point from which the pursued has just departed, so that the slower must necessarily be always still more or less in advance." Physics, Book 6, Chapter 9, 239b, RP 137. End of footnote 2. This argument is essentially the same as the previous one. It shows that if Achilles ever overtakes the tortoise, it must be after an infinite number of instants have elapsed since he started. This is, in fact, true. But the view that an infinite number of instants make up an infinitely long time is not true, and therefore the conclusion that Achilles will never overtake the tortoise does not follow. The third argument, footnote 3, Physics, Book 6, Chapter 9, 239b, RP, page 138, end of footnote 3. That of the arrow is very interesting. The text has been questioned. Burnet accepts the alterations of Zeller and paraphrases thus. The arrow in flight is at rest, for if everything is at rest when it occupies a space equal to itself, and what is in flight at any given moment always occupies a space equal to itself, it cannot move. But according to Prantl, the literal translation of the unamended text of Aristotle's statement of the argument is as follows. If everything, when it is behaving in a uniform manner, is continually either moving or at rest, but what is moving is always in the now, then the moving arrow is motionless. This form of the argument brings out its force more clearly than Burnet's paraphrase. Here, if not in the first two arguments, the view that a finite part of time consists of a finite series of successive instants seems to be assumed. At any rate, the plausibility of the argument seems to depend upon supposing that there are consecutive instants. Throughout an instant, it is said, a moving body is where it is. It cannot move during the instant, for that would require that the instant should have parts. Thus, suppose we consider a period consisting of 1,000 instants, and suppose the arrow is in flight throughout this period. At each of the 1,000 instants, the arrow is where it is, though at the next instant it is somewhere else. It is never moving, but in some miraculous way, the change of position has to occur between the instants. That is to say, not at any time whatever. This is what M. Bergson calls the cinematographic representation of reality. The more the difficulty is meditated, the more real it becomes. The solution lies in the theory of continuous series. We find it hard to avoid supposing that, when the arrow is in flight, there is a next position occupied at the next moment. But in fact, there is no next position and no next moment. And when once this is imaginatively realized, the difficulty is seen to disappear. The fourth and last of Zeno's arguments is, footnote 1, Physics, Book 6, Chapter 9, 239b, RP, page 139, end of footnote 1. The argument of the stadium. The argument as stated by Burnet is as follows. Half the time may be equal to double the time. Let us suppose 3 rows of bodies, one of which A is at rest, while the other two, B, C, are moving with equal velocity in opposite directions. By the time they are all in the same part of the course, B will have passed twice as many of the bodies in C as in A. Therefore, the time which it takes to pass C is twice as long as the time it takes to pass A. But the time which B and C take to reach the position of A is the same. Therefore, double the time is equal to the half. Gay, footnote 2, local citation, end of footnote 2, devoted an interesting article to the interpretation of this argument. His translation of Aristotle's statement is as follows. The fourth argument is that concerning the two rows of bodies, each row being composed of an equal number of bodies of equal size, passing each other on a race course as they proceed with equal velocity in opposite directions, the one row originally occupying the space between the goal and the middle point of the course, and the other that between the middle point and the starting post. This, he thinks, involves the conclusion that half a given time is equal to double the time. The fallacy of the reasoning lies in the assumption that a body occupies an equal time in passing with equal velocity a body that is in motion and a body of equal size that is at rest, an assumption which is false. For instance, so runs the argument, let AA be the stationary bodies of equal size, and BB the bodies equal in number and in size to AA, originally occupying the half of the course from the starting post to the middle of the A's, and CC those originally occupying the other half from the goal to the middle of the A's, equal in number, size, and velocity, to BB. Then three consequences follow. First, as the B's and C's pass one another, the first B reaches the last C at the same moment at which the first C reaches the last B. Secondly, at this moment, the first C has passed all the A's, whereas the first B has passed only half the A's, and has consequently occupied only half the time occupied by the first C, since each of the two occupies an equal time in passing each A. Thirdly, at the same moment, all the B's have passed all the C's, for the first C and the first B will simultaneously reach the opposite ends of the course, since, so says Zeno, the time occupied by the first C in passing each of the B's is equal to that occupied by it in passing each of the A's, because an equal time is occupied by both the first B and the first C in passing all the A's. This is the argument, but it presupposes the aforesaid fallacious assumption. This argument is not quite easy to follow, and it is only valid as against the assumption that a finite time consists of a finite number of instants. We may restate it in different language. Let us suppose three drill sergeants, A', and A', standing in a row, while the two files of soldiers march past them in opposite directions. At the first moment which we consider, the three men B, B', B" in one row, and the three men C, C', C" in the other row, are respectively opposite to A', and A'. At the very next moment, each row has moved on, and now B and C" are opposite A'. Thus, B and C" are opposite each other. When, then, did B pass C'? It must have been somewhere between the two moments which we supposed consecutive, and therefore the two moments cannot really have been consecutive. It follows that there must be other moments between any two given moments, and therefore that there must be an infinite number of moments in any given interval of time. The above difficulty, that B must have passed C' at some time between two consecutive moments, is a genuine one, but it is not precisely the difficulty raised by Zeno. What Zeno professes to prove is that half of a given time is equal to double that time. The most intelligible explanation of the argument known to me is that of Gay. Footnote 1, local citation, page 105, end of footnote 1. Since, however, his explanation is not easy to set forth shortly, I will restate what seems to me to be the logical essence of Zeno's contention. If we suppose that time consists of a series of consecutive instants, and that motion consists in passing through a series of consecutive points, then the fastest possible motion is one which at each instant is at a point consecutive to that at which it was at the previous instant. Any slower motion must be one which has intervals of rest interspersed, and any faster motion must wholly omit some points. All this is evident from the fact that we cannot have more than one event for each instant. But now, in the case of our A's and B's and C's, B is opposite a fresh A every instant, and therefore the number of A's passed gives the number of instants since the beginning of the motion. But during the motion, B has passed twice as many C's, and yet cannot have passed more than one each instant. Hence the number of instants since the motion began is twice the number of A's passed, though we previously found it was equal to this number. From this result, Zeno's conclusion follows. Zeno's arguments in some form have afforded grounds for almost all the theories of space and time and infinity which have been constructed from his day to our own. We have seen that all his arguments are valid, with certain reasonable hypotheses, on the assumption that finite spaces and times consist of a finite number of points and instants, and that the third and fourth almost certainly in fact proceeded on this assumption, while the first and second, which were perhaps intended to refute the opposite assumption, were in that case fallacious. We may therefore escape from his paradoxes either by maintaining that, though space and time do consist of points and instants, the number of them in any finite interval is infinite, or by denying that space and time consist of points and instants at all, or lastly, by denying the reality of space and time altogether. It would seem that Zeno himself, as a supporter of Parmenides, drew the last of these three possible deductions, at any rate in regard to time. In this a very large number of philosophers have followed him. Many others, like M. Bergson, have preferred to deny that space and time consist of points and instants. Either of these solutions will meet the difficulties in the form in which Zeno raised them. But as we saw, the difficulties can also be met if infinite numbers are admissible, and on grounds which are independent of space and time, infinite numbers and series in which no two terms are consecutive must in any case be admitted. Consider, for example, all the fractions less than 1, arranged in order of magnitude. Between any two of them there are others, for example, the arithmetical mean of the two. Thus no two fractions are consecutive, and the total number of them is infinite. It will be found that much of what Zeno says as regards the series of points on a line can be equally well applied to the series of fractions, and we cannot deny that there are fractions, so that two of the above ways of escape are closed to us. It follows that, if we are to solve the whole class of difficulties derivable from Zeno's by analogy, we must discover some tenable theory of infinite numbers. What, then, are the difficulties which, until the last 30 years, led philosophers to the belief that infinite numbers are impossible? The difficulties of infinity are of two kinds, of which the first may be called sham, while the others involve, for their solution, a certain amount of new and not altogether easy thinking. The sham difficulties are those suggested by the etymology, and those suggested by confusion of the mathematical infinite with what philosophers impertinently call the true infinite. Etymologically, infinite should mean having no end. But in fact, some infinite series have ends, some have not. While some collections are infinite without being serial, and can therefore not properly be regarded as either endless or having ends. The series of instants from any earlier one to any later one, both included, is infinite, but has two ends. The series of instants from the beginning of time to the present moment has one end, but is infinite. Kant, in his first antinomy, seems to hold that it is harder for the past to be infinite than for the future to be so, on the ground that the past is now completed, and that nothing infinite can be completed. It is very difficult to see how he can have imagined that there was any sense in this remark, but it seems most probable that he was thinking of the infinite as the unended. It is odd that he did not see that the future too has one end at the present, and is precisely on a level with the past. His regarding the two as different in this respect illustrates just that kind of slavery to time which we agreed in speaking of Parmenides, the true philosopher must learn to leave behind him. The confusions introduced into the notions of philosophers by the so-called true infinite are curious. They see that this notion is not the same as the mathematical infinite, but they choose to believe that it is the notion which the mathematicians are vainly trying to reach. They therefore inform the mathematicians, kindly but firmly, that they are mistaken in adhering to the false infinite, since plainly the true infinite is something quite different. The reply to this is that what they call the true infinite is a notion totally irrelevant to the problem of the mathematical infinite, to which it has only a fanciful and verbal analogy. So remote is it that I do not propose to confuse the issue by even mentioning what the true infinite is. It is the false infinite that concerns us, and we have to show that the epithet false is undeserved. There are, however, certain genuine difficulties in understanding the infinite, certain habits of mind derived from consideration of finite numbers, and easily extended to infinite numbers under the mistaken notion that they represent logical necessities. For example, every number that we are accustomed to, except 0, has another number immediately before it, from which it results by adding 1. But the first infinite number does not have this property. The numbers before it form an infinite series, containing all the ordinary finite numbers, having no maximum, no last finite number, after which one little step would plunge us into the infinite. If it is assumed that the first infinite number is reached by a succession of small steps, it is easy to show that it is self-contradictory. The first infinite number is, in fact, beyond the whole unending series of finite numbers. But, it will be said, there cannot be anything beyond the whole of an unending series. This, we may point out, is the very principle upon which Zeno relies in the arguments of the race course and the Achilles. Take the race course. There is the moment when the runner still has half his distance to run, then the moment when he still has a quarter, then when he still has an eighth, and so on in a strictly unending series. Beyond the whole of this series is the moment when he reaches the goal. Thus, there certainly can be something beyond the whole of an unending series. But it remains to show that this fact is only what might have been expected. The difficulty, like most of the vaguer difficulties besetting the mathematical infinite, is derived, I think, from the more or less unconscious operation of the idea of counting. If you set to work to count the terms in an infinite collection, you will never have completed your task. Thus, in the case of the runner, if half, 3/4, 7/8, and so on of the course were marked, and the runner was not allowed to pass any of the marks until the umpire said now, then Zeno's conclusion would be true in practice, and he would never reach the goal. But it is not essential to the existence of a collection, or even to knowledge and reasoning concerning it, that we should be able to pass its terms in review one by one. This may be seen in the case of finite collections. We can speak of mankind or the human race, though many of the individuals in this collection are not personally known to us. We can do this because we know of various characteristics which every individual has if he belongs to the collection, and not if he does not. And exactly the same happens in the case of infinite collections. They may be known by their characteristics, although their terms cannot be enumerated. In this sense, an unending series may nevertheless form a whole, and there may be new terms beyond the whole of it. Some purely arithmetical peculiarities of infinite numbers have also caused perplexity. For instance, an infinite number is not increased by adding 1 to it or by doubling it. Such peculiarities have seemed to many to contradict logic, but in fact they only contradict confirmed mental habits. The whole difficulty of the subject lies in the necessity of thinking in an unfamiliar way, and in realizing that many properties which we have thought inherent in number are in fact peculiar to finite numbers. If this is remembered, the positive theory of infinity, which will occupy the next lecture, will not be found so difficult as it is to those who cling obstinately to the prejudices instilled by the arithmetic which is learnt in childhood. End of Lecture 6. A difficult question, partly concerned with the use of words, but partly also of real importance in understanding the function of philosophy. Every subject matter, it would seem, can give rise to philosophical investigations as well as to the appropriate science, the difference between the two treatments being in the direction of movement in the kind of truths which it is sought to establish. In the special sciences, when they have become fully developed, the movement is forward and synthetic, from the simpler to the more complex. But in philosophy we follow the inverse direction. From the complex and relatively concrete, we proceed towards the simple and abstract by means of analysis, seeking in the process to eliminate the particularity of the original subject matter, and to confine our attention entirely to the logical form of the facts concerned. Between philosophy and pure mathematics there is a certain affinity, in the fact that both are general and a priori. Neither of them asserts propositions which, like those of history and geography, depend upon the actual concrete facts being just what they are. We may illustrate this characteristic by means of Leibniz's conception of many possible worlds, of which only one is actual. In all the many possible worlds, philosophy and mathematics will be the same. The differences will only be in respect of those particular facts which are chronicled by the descriptive sciences. Any quality, therefore, by which our actual world is distinguished from other abstractly possible worlds must be ignored by mathematics and philosophy alike. Mathematics and philosophy differ, however, in their manner of treating the general properties in which all possible worlds agree. For while mathematics, starting from comparatively simple propositions, seeks to build up more and more complex results by deductive synthesis, philosophy, starting from data which are common knowledge, seeks to purify and generalize them into the simplest statements of abstract form that can be obtained from them by logical analysis. The difference between philosophy and mathematics may be illustrated by our present problem, namely, the nature of number. Both start from certain facts about numbers which are evident to inspection, but mathematics uses these facts to deduce more and more complicated theorems, while philosophy seeks, by analysis, to go behind these facts to others, simpler, more fundamental, and inherently more fitted to form the premises of the science of arithmetic. The question, what is a number, is the preeminent philosophic question in this subject, but it is one which the mathematician as such need not ask, provided he knows enough of the properties of numbers to enable him to deduce his theorems. We, since our subject is philosophical, must grapple with the philosopher's question. The answer to the question, what is a number, which we shall reach in this lecture, will be found to give also, by implication, the answer to the difficulties of infinity which we considered in the previous lecture. The question, what is a number, is one which until quite recent times was never considered in the kind of way that is capable of yielding a precise answer. Philosophers were content with some vague dictum, such as "number is unity in plurality." A typical definition of the kind that contented philosophers is the following from Sigwart's Logic, section 66, section 3. Every number is not merely a plurality, but a plurality thought as held together and closed, and to that extent as a unity. Now there is in such definitions a very elementary blunder, of the same kind that would be committed if we said yellow is a flower because some flowers are yellow. Take, for example, the number 3. A single collection of 3 things might conceivably be described as a plurality thought as held together and closed, and to that extent as a unity. But a collection of 3 things is not the number 3. The number 3 is something which all collections of 3 things have in common, but is not itself a collection of 3 things. The definition, therefore, apart from any other defects, has failed to reach the necessary degree of abstraction. The number 3 is something more abstract than any collection of 3 things. Such vague philosophic definitions, however, remained inoperative because of their very vagueness. What most men who thought about numbers really had in mind was that numbers are the result of counting. On the consciousness of the law of counting, says Sigwart at the beginning of his discussion of number, rests the possibility of spontaneously prolonging the series of numbers ad infinitum. It is this view of number as generated by counting which has been the chief psychological obstacle to the understanding of infinite numbers. Counting, because it is familiar, is erroneously supposed to be simple, whereas it is in fact a highly complex process, which has no meaning unless the numbers reached in counting have some significance independent of the process by which they are reached. And infinite numbers cannot be reached at all in this way. The mistake is of the same kind as if cows were defined as what can be bought from a cattle merchant. To a person who knew several cattle merchants but had never seen a cow, this might seem an admirable definition. But if in his travels he came across a herd of wild cows, he would have to declare that they are not cows at all, because no cattle merchant could sell them. So infinite numbers were declared not to be numbers at all, because they could not be reached by counting. It will be worthwhile to consider for a moment what counting actually is. We count a set of objects when we let our attention pass from one to another, until we have attended once to each, saying the names of the numbers in order, with each successive act of attention. The last number named in this process is the number of the objects, and therefore counting is a method of finding out what the number of objects is. But this operation is really a very complicated one, and those who imagine that it is the logical source of number show themselves remarkably incapable of analysis. In the first place, when we say 1, 2, 3 as we count, we cannot be said to be discovering the number of the objects counted, unless we attach some meaning to the words 1, 2, 3. A child may learn to know these words in order, and to repeat them correctly, like the letters of the alphabet, without attaching any meaning to them. Such a child may count correctly from the point of view of a grown-up listener, without having any idea of numbers at all. The operation of counting, in fact, can only be intelligently performed by a person who already has some idea what the numbers are. And from this it follows that counting does not give the logical basis of number. Again, how do we know that the last number reached in the process of counting is the number of the objects counted? This is just one of those facts that are too familiar for their significance to be realized. But those who wish to be logicians must acquire the habit of dwelling upon such facts. There are 2 propositions involved in this fact. First, that the number of numbers from 1 up to any given number is that given number. For instance, the number of numbers from 1 to 100 is 100. Secondly, that if a set of numbers can be used as names of a set of objects, each number occurring only once, then the number of numbers used as names is the same as the number of objects. The first of these propositions is capable of an easy arithmetical proof, so long as finite numbers are concerned. but with infinite numbers after the first, it ceases to be true. The second proposition remains true, and is, in fact, as we shall see, an immediate consequence of the definition of number. But owing to the falsehood of the first proposition, where infinite numbers are concerned, counting, even if it were practically possible, would not be a valid method of discovering the number of terms in an infinite collection, and would in fact give different results according to the manner in which it was carried out. There are two respects in which the infinite numbers that are known differ from finite numbers. First, infinite numbers have, while finite numbers have not, a property which I shall call reflexiveness. Secondly, finite numbers have, while infinite numbers have not, a property which I shall call inductiveness. Let us consider these two properties successively. 1. Reflexiveness. A number is said to be reflexive when it is not increased by adding 1 to it. It follows at once that any finite number can be added to a reflexive number without increasing it. This property of infinite numbers was always thought, until recently, to be self-contradictory. But through the work of Georg Cantor, it has come to be recognized that, though at first astonishing, it is no more self-contradictory than the fact that people at the antipodes do not tumble off. In virtue of this property, given any infinite collection of objects, any finite number of objects can be added or taken away without increasing or diminishing the number of the collection. Even an infinite number of objects may, under certain conditions, be added or taken away without altering the number. This may be made clearer by the help of some examples. Imagine all the natural numbers 0, 1, 2, 3, and so on to be written down in a row, and immediately beneath them write down the numbers 1, 2, 3, 4, and so on, so that 1 is under 0, 2 is under 1, and so on. Then every number in the top row has a number directly under it in the bottom row, and no number occurs twice in either row. It follows that the number of numbers in the two rows must be the same. But all the numbers that occur in the bottom row also occur in the top row, and one more, namely 0. Thus, the number of terms in the top row is obtained by adding 1 to the number of the bottom row. So long, therefore, as it was supposed that a number must be increased by adding 1 to it, this state of things constituted a contradiction, and led to the denial that there are infinite numbers. The following example is even more surprising. Write the natural numbers 1, 2, 3, 4, and so on in the top row, and the even numbers 2, 4, 6, 8, and so on in the bottom row, so that under each number in the top row stands its double in the bottom row. Then, as before, the number of numbers in the two rows is the same, yet the second row results from taking away all the odd numbers, an infinite collection, from the top row. This example is given by Leibniz to prove that there can be no infinite numbers. He believed in infinite collections, but, since he thought that a number must always be increased when it is added to and diminished when it is subtracted from, he maintained that infinite collections do not have numbers. The number of all numbers, he says, implies a contradiction, which I show thus. To any number there is a corresponding number equal to its double. Therefore, the number of all numbers is not greater than the number of even numbers, that is, the whole is not greater than its part. Footnote 1, Philosophical Works, Gerhardt's edition, Volume 1, page 338. End of footnote 1. In dealing with this argument, we ought to substitute the number of all finite numbers for the number of all numbers. We then obtain exactly the illustration given by our two rows, one containing all the finite numbers, the other only the even finite numbers. It will be seen that Leibniz regards it as self-contradictory to maintain that the whole is not greater than its part. But the word greater is one which is capable of many meanings. For our purpose, we must substitute the less ambiguous phrase containing a greater number of terms. In this sense, it is not self-contradictory for whole and part to be equal. It is the realization of this fact which has made the modern theory of infinity possible. There is an interesting discussion of the reflexiveness of infinite wholes in the first of Galileo's dialogues on motion. I quote from a translation published in 1730. Footnote 1. Mathematical Discourses Concerning Two New Sciences Relating to Mechanics and Local Motion, in 4 dialogues, by Galileo Galilei, chief philosopher and mathematician to the Grand Duke of Tuscany, done into English from the Italian by Tho Weston, late Master, and now published by John Weston, present Master, of the Academy at Greenwich. See pages 46 and following. End of footnote 1. The personages in the dialogue are Salviati, Sagredo, and Simplicius, and they reason as follows. Simplicius. Here already arises a doubt which I think is not to be resolved, and that is this. Since 'tis plain that one line is given greater than another, and since both contain infinite points, we must surely necessarily infer that we have found in the same species something greater than infinite, since the infinity of points of the greater line exceeds the infinity of points of the lesser. But now to assign an infinite greater than an infinite is what I can't possibly conceive. Salviati. These are some of those difficulties which arise from discourses which our finite understanding makes about infinites, by ascribing to them attributes which we give to things finite and terminate, which I think most improper, because those attributes of majority, minority, and equality agree not with infinities, of which we can't say that one is greater than, less than, or equal to another. For proof whereof I have something come into my head, which, that I may be the better understood, I will propose by way of interrogatories to Simplicius, who started this difficulty. To begin, then, I suppose you know which are square numbers and which not? Simplicius. I know very well that a square number is that which arises from the multiplication of any number into itself. Thus 4 and 9 are square numbers, that arising from 2, and this from 3, multiplied by themselves. Salviati. Very well, and you also know that as the products are called squares, the factors are called roots, and that the other numbers which proceed not from squares multiplied into themselves are not squares. Whence, taking in all numbers, both squares and not squares, if I should say that the not squares are more than the squares, should I not be in the right? Simplicius. Most certainly. Salviati. If I go on with you then, and ask you, how many squared numbers are there, you may truly answer that there are as many as are their proper roots, since every square has its own root, and every root has its own square. And since no square has more than one root, nor any root more than one square. Simplicius. Very true. Salviati. But now, if I should ask how many roots there are, you can't deny but there are as many as there are numbers, since there's no number but what's the root to some square. And this being granted, we may likewise affirm that there are as many square numbers as there are numbers, for there are as many squares as there are roots, and as many roots as numbers. And yet in the beginning of this we said there were many more numbers than squares, the greater part of numbers being not squares. And though the number of squares decreases in a greater proportion as we go on to bigger numbers, for count to 100, you'll find 10 squares, namely 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, which is the same as to say the 10th part are squares, in 10,000 only the 100th part are squares, in 1,000,000 only the 1,000th. And yet in an infinite number, if we can but comprehend it, we may say the squares are as many as all the numbers taken together. Sagredo. What must be determined then in this case? Salviati. I see no other way, but by saying that all numbers are infinite. Squares are infinite, their roots are infinite, and that the number of squares is not less than the number of numbers, nor this less than that. And then by concluding that the attributes or terms of equality, majority, and minority have no place in infinities, but are confined to terminate quantities. The way in which the problem is expounded in the above discussion is worthy of Galileo, but the solution suggested is not the right one. It is actually the case that the number of square finite numbers is the same as the number of finite numbers. The fact that, so long as we confine ourselves to numbers less than some given finite number, the proportion of squares tends towards 0 as the given finite number increases, does not contradict the fact that the number of all finite numbers is the same as the number of all finite squares. This is only an instance of the fact, now familiar to mathematicians, that the limit of a function as the variable approaches a given point may not be the same as its value when the variable actually reaches the given point. But although the infinite numbers which Galileo discusses are equal, Cantor has shown that what Simplicius could not conceive is true, namely, that there are an infinite number of different infinite numbers, and that the conception of greater and less can be perfectly well applied to them. The whole of Simplicius's difficulty comes, as is evident, from his belief that, if greater and less can be applied, a part of an infinite collection must have fewer terms than the whole. And when this is denied, all contradictions disappear. As regards greater and less lengths of lines, which is the problem from which the above discussion starts, that involves a meaning of greater and less which is not arithmetical. The number of points is the same in a long line and in a short one, being in fact the same as the number of points in all space. The greater and less of metrical geometry involves the new metrical conception of congruence, which cannot be developed out of arithmetical considerations alone. But this question has not the fundamental importance which belongs to the arithmetical theory of infinity. Non-inductiveness. The second property by which infinite numbers are distinguished from finite numbers is the property of non-inductiveness. This will be best explained by defining the positive property of inductiveness which characterizes the finite numbers, and which is named after the method of proof known as mathematical induction. Let us first consider what is meant by calling a property hereditary in a given series. Take such a property as being named Jones. If a man is named Jones, so is his son. We will therefore call the property of being called Jones hereditary, with respect to the relation of father and son. If a man is called Jones, all his descendants in the direct male line are called Jones. This follows from the fact that the property is hereditary. Now, instead of the relation of father and son, consider the relation of a finite number to its immediate successor, that is, the relation which holds between 0 and 1, between 1 and 2, between 2 and 3, and so on. If a property of numbers is hereditary with respect to this relation, then if it belongs to, say, 100, it must belong also to all finite numbers greater than 100. For, being hereditary, it belongs to 101 because it belongs to 100, and it belongs to 102 because it belongs to 101, and so on, where the "and so on" will take us, sooner or later, to any finite number greater than 100. Thus, for example, the property of being greater than 99 is hereditary in the series of finite numbers, and generally, a property is hereditary in this series when, given any number that possesses the property, the next number must always also possess it. It will be seen that a hereditary property, though it must belong to all the finite numbers greater than a given number possessing the property, need not belong to all the numbers less than this number. For example, the hereditary property of being greater than 99 belongs to 100 and all greater numbers, but not to any smaller number. Similarly, the hereditary property of being called Jones belongs to all the descendants in the direct male line of those who have this property, but not to all their ancestors, because we reach at last a first Jones, before whom the ancestors have no surname. It is obvious, however, that any hereditary property possessed by Adam must belong to all men, and similarly any hereditary property possessed by 0 must belong to all finite numbers. This is the principle of what is called mathematical induction. It frequently happens, when we wish to prove that all finite numbers have some property, that we have first to prove that zero has the property, and then that the property is hereditary, that is, that if it belongs to a given number, then it belongs to the next number, owing to the fact that such proofs are called inductive. I shall call the properties to which they are applicable inductive properties. Thus, an inductive property of numbers is one which is hereditary and belongs to zero. Taking any one of the natural numbers, say 29, it is easy to see that it must have all inductive properties. For since such properties belong to zero and are hereditary, they belong to 1. Therefore, since they are hereditary, they belong to 2, and so on. By 29 repetitions of such arguments, we show that they belong to 29. We may define the inductive numbers as all those that possess all inductive properties. They will be the same as what are called the natural numbers, that is, the ordinary finite whole numbers. To all such numbers, proofs by mathematical induction can be validly applied. They are those numbers, we may loosely say, which can be reached from zero by successive additions of 1. In other words, they are all the numbers that can be reached by counting. But beyond all these numbers, there are the infinite numbers, and infinite numbers do not have all inductive properties. Such numbers, therefore, may be called non-inductive. All those properties of numbers which are proved by an imaginary step-by-step process from one number to the next are liable to fail when we come to infinite numbers. The first of the infinite numbers has no immediate predecessor, because there is no greatest finite number. Thus, no succession of steps from one number to the next will ever reach from a finite number to an infinite one, and the step-by-step method of proof fails. This is another reason for the supposed self-contradictions of infinite number. Many of the most familiar properties of numbers, which custom had led people to regard as logically necessary, are in fact only demonstrable by the step-by-step method, and fail to be true of infinite numbers. But as soon as we realize the necessity of proving such properties by mathematical induction, and the strictly limited scope of this method of proof, the supposed contradictions are seen to contradict not logic, but only our prejudices and mental habits. The property of being increased by the addition of 1, that is, the property of non-reflexiveness, may serve to illustrate the limitations of mathematical induction. It is easy to prove that 0 is increased by the addition of 1, and that if a given number is increased by the addition of 1, so is the next number, that is, the number obtained by the addition of 1. It follows that each of the natural numbers is increased by the addition of 1. This follows generally from the general argument, and follows for each particular case by a sufficient number of applications of the argument. We first prove that 0 is not equal to 1. Then, since the property of being increased by 1 is hereditary, it follows that 1 is not equal to 2. Hence it follows that 2 is not equal to 3. If we wish to prove that 30,000 is not equal to 30,001, we can do so by repeating this reasoning 30,000 times. But we cannot prove in this way that all numbers are increased by the addition of 1. We can only prove that this holds of the numbers attainable by successive additions of 1, starting from 0. The reflexive numbers which lie beyond all those attainable in this way are, as a matter of fact, not increased by the addition of 1. The two properties of reflexiveness and non-inductiveness, which we have considered as characteristics of infinite numbers, have not so far been proved to be always found together. It is known that all reflexive numbers are non-inductive, but it is not known that all non-inductive numbers are reflexive. Fallacious proofs of this proposition have been published by many writers, including myself, but up to the present no valid proof has been discovered. The infinite numbers actually known, however, are all reflexive as well as non-inductive. Thus, in mathematical practice, if not in theory, the two properties are always associated. For our purposes, therefore, it will be convenient to ignore the bare possibility that there may be non-inductive, non-reflexive numbers, since all known numbers are either inductive or reflexive. When infinite numbers are first introduced to people, they are apt to refuse the name of numbers to them, because their behavior is so different from that of finite numbers that it seems a willful misuse of terms to call them numbers at all. In order to meet this feeling, we must now turn to the logical basis of arithmetic and consider the logical definition of numbers. The logical definition of numbers, though it seems an essential support to the theory of infinite numbers, was in fact discovered independently and by a different man. The theory of infinite numbers, that is to say, the arithmetical as opposed to the logical part of the theory, was discovered by Georg Cantor and published by him in 1882 to 1883. Footnote 1. In his Grundlagen einer allgemeinen Mannigfaltigkeitslehre and in his articles in Acta Mathematica, Volume 2. End of footnote 1. The definition of number was discovered about the same time by a man whose great genius has not received the recognition it deserves. I mean Gottlob Frege of Jena. His first work, Begriffsschrift, published in 1879, contained the very important theory of hereditary properties in a series to which I alluded in connection with inductiveness. His definition of number is contained in his second work, published in 1884, and entitled Die Grundlagen der Arithmetik, eine logisch-mathematische Untersuchung über den Begriff der Zahl. Footnote 2. The definition of number contained in this book, and elaborated in the Grundgesetz der Arithmetik, Volume 1, 1893, Volume 2, 1903, was rediscovered by me in ignorance of Frege's work. I wish to state as emphatically as possible what seems still often ignored, that his discovery antedated mine by 18 years. End of footnote 2. It is with this book that the logical theory of arithmetic begins, and it will repay us to consider Frege's analysis in some detail. Frege begins by noting the increased desire for logical strictness in mathematical demonstrations, which distinguishes modern mathematicians from their predecessors, and points out that this must lead to a critical investigation of the definition of number. He proceeds to show the inadequacy of previous philosophical theories, especially of the synthetic a priori theory of Kant and the empirical theory of Mill. This brings him to the question, what kind of object is it that number can properly be ascribed to? He points out that physical things may be regarded as one or many. For example, if a tree has 1,000 leaves, they may be taken together as constituting its foliage, which would count as one, not as 1,000. And one pair of boots is the same object as 2 boots. It follows that physical things are not the subjects of which number is properly predicated. For when we have discovered the proper subjects, the number to be ascribed must be unambiguous. This leads to a discussion of the very prevalent view that number is really something psychological and subjective, a view which Frege emphatically rejects. Number, he says, is as little an object of psychology or an outcome of psychical processes as the North Sea. The botanist wishes to state something which is just as much a fact when he gives the number of petals in a flower as when he gives its color. The one depends as little as the other upon our caprice. There is, therefore, a certain similarity between number and color, but this does not consist in the fact that both are sensibly perceptible in external things, but in the fact that both are objective. Page 34. I distinguish the objective, he continues, from the palpable, the spatial, the actual. The Earth's axis, the center of mass of the solar system, are objective, but I should not call them actual, like the Earth itself. Page 35. He concludes that number is neither spatial and physical, nor subjective, but nonsensible and objective. The conclusion is important since it applies to all the subject matter of mathematics and logic. Most philosophers have thought that the physical and the mental, between them, exhausted the world of being. Some have argued that the objects of mathematics were obviously not subjective, and therefore must be physical and empirical. Others have argued that they were obviously not physical, and therefore must be subjective and mental. Both sides were right in what they denied, and wrong in what they asserted. Frege has the merit of accepting both denials and finding a third assertion by recognizing the world of logic, which is neither mental nor physical. The fact is, as Frege points out, that no number, not even one, is applicable to physical things, but only to general terms or descriptions, such as man, satellite of the Earth, satellite of Venus. The general term man is applicable to a certain number of objects. There are in the world so and so many men. The unity which philosophers rightly feel to be necessary for the assertion of a number is the unity of the general term, and it is the general term which is the proper subject of number. And this applies equally when there is one object or none which falls under the general term. Satellite of the Earth is a term only applicable to one object, namely the moon. But one is not a property of the moon itself, which may equally well be regarded as many molecules. It is a property of the general term Earth's satellite. Similarly, 0 is a property of the general term satellite of Venus, because Venus has no satellite. Here at last we have an intelligible theory of the number 0. This was impossible if numbers applied to physical objects, because obviously no physical object could have the number 0. Thus, in seeking our definition of number, we have arrived so far at the result that numbers are properties of general terms or general descriptions, not of physical things or of mental occurrences. Instead of speaking of a general term, such as man, as the subject of which a number can be asserted, we may, without making any serious change, take the subject as the class or collection of objects, that is, mankind in the above instance, to which the general term in question is applicable. Two general terms, such as man and featherless biped, which are applicable to the same collection of objects, will obviously have the same number of instances. Thus, the number depends upon the class, not upon the selection of this or that general term to describe it, provided several general terms can be found to describe the same class. But some general term is always necessary in order to describe a class. Even when the terms are enumerated, as this and that and the other, the collection is constituted by the general property of being either this or that or the other, and only so acquires the unity which enables us to speak of it as one collection. And in the case of an infinite class, enumeration is impossible, so that description by a general characteristic, common and peculiar, to the members of the class is the only possible description. Here, as we see, the theory of number to which Frege was led by purely logical considerations becomes of use in showing how infinite classes can be amenable to number, in spite of being incapable of enumeration. Frege next asks the question, when do two collections have the same number of terms? In ordinary life, we decide this question by counting. But counting, as we saw, is impossible in the case of infinite collections, and is not logically fundamental with finite collections. We want, therefore, a different method of answering our question. An illustration may help to make the method clear. I do not know how many married men there are in England, but I do know that the number is the same as the number of married women. The reason I know this is that the relation of husband and wife relates one man to one woman and one woman to one man. A relation of this sort is called a one-one relation. The relation of father to son is called a one-many relation because a man can have only one father, but may have many sons. Conversely, the relation of son to father is called a many-one relation. But the relation of husband to wife in Christian countries is called one-one because a man cannot have more than one wife, or a woman more than one husband. Now, whenever there is a one-one relation between all the terms of one collection and all the terms of another severally, as in the case of English husbands and English wives, the number of terms in the one collection is the same as the number in the other. But when there is not such a relation, the number is different. This is the answer to the question, when do two collections have the same number of terms? We can now, at last, answer the question, what is meant by the number of terms in a given collection? When there is a one-one relation between all the terms of one collection and all the terms of another severally, we shall say that the two collections are similar. We have just seen that two similar collections have the same number of terms. This leads us to define the number of a given collection as the class of all collections that are similar to it. That is to say, we set up the following formal definition. The number of terms in a given class is defined as meaning the class of all classes that are similar to the given class. This definition, as Frege, expressing it in slightly different terms, showed, yields the usual arithmetical properties of numbers. It is applicable equally to finite and infinite numbers, and it does not require the admission of some new and mysterious set of metaphysical entities. It shows that it is not physical objects, but classes or the general terms by which they are defined, of which numbers can be asserted. And it applies to 0 and 1 without any of the difficulties which other theories find in dealing with these two special cases. The above definition is sure to produce, at first sight, a feeling of oddity, which is liable to cause a certain dissatisfaction. It defines the number 2, for instance, as the class of all couples, and the number 3 as the class of all triads. This does not seem to be what we have hitherto been meaning when we spoke of 2 and 3, though it would be difficult to say what we had been meaning. The answer to a feeling cannot be a logical argument, but nevertheless the answer in this case is not without importance. In the first place, it will be found that when an idea has grown familiar as an unanalyzed whole is first resolved accurately into its component parts, which is what we do when we define it, there is almost always a feeling of unfamiliarity produced by the analysis, which tends to cause a protest against the definition. In the second place, it may be admitted that the definition, like all definitions, is to a certain extent arbitrary. In the case of the small finite numbers, such as 2 and 3, it would be possible to frame definitions more nearly in accordance with our unanalyzed feeling of what we mean. But the method of such definitions would lack uniformity, and would be found to fail sooner or later, at latest when we reached infinite numbers. In the third place, the real desideratum about such a definition as that of number is not that it should represent as nearly as possible the ideas of those who have not gone through the analysis required in order to reach a definition, but that it should give us objects having the requisite properties. Numbers, in fact, must satisfy the formulae of arithmetic. Any indubitable set of objects fulfilling this requirement may be called numbers. So far, the simplest set known to fulfill this requirement is the set introduced by the above definition. In comparison with this merit, the question whether the objects to which the definition applies are like or unlike the vague ideas of numbers entertained by those who cannot give a definition is one of very little importance. All the important requirements are fulfilled by the above definition, and the sense of oddity, which is at first unavoidable, will be found to wear off very quickly with the growth of familiarity. There is, however, a certain logical doctrine which may be thought to form an objection to the above definition of numbers as classes of classes. I mean the doctrine that there are no such objects as classes at all. It might be thought that this doctrine would make havoc of a theory which reduces numbers to classes, and of the many other theories in which we have made use of classes. This, however, would be a mistake. None of these theories are any the worse for the doctrine that classes are fictions. What the doctrine is and why it is not destructive, I will try briefly to explain. On account of certain rather complicated difficulties, culminating in definite contradictions, I was led to the view that nothing that can be said significantly about things, that is, particulars, can be said significantly, that is, either truly or falsely, about classes of things. That is to say, if in any sentence in which a thing is mentioned you substitute a class for the thing, you no longer have a sentence that has any meaning. The sentence is no longer either true or false, but a meaningless collection of words. Appearances to the contrary can be dispelled by a moment's reflection. For example, in the sentence, Adam is fond of apples, you may substitute mankind and say, mankind is fond of apples. But obviously you do not mean that there is one individual called mankind which munches apples. You mean that the separate individuals who compose mankind are each severally fond of apples. Now, if nothing that can be said significantly about a thing can be said significantly about a class of things, it follows that classes of things cannot have the same kind of reality as things have. For if they had, a class could be substituted for a thing in a proposition predicating the kind of reality which would be common to both. This view is really consonant to common sense. In the 3rd or 4th century BC, there lived a Chinese philosopher named Hu who maintained that a bay horse and a dun cow are 3, because taken separately they are 2, and taken together they are 1. 2 and 1 make 3. Footnote 1, Giles, The Civilization of China, Home University Library, page 147. End of footnote 1. The author from whom I quote says that Hu was particularly fond of the quibbles which so delighted the sophists or unsound reasoners of ancient Greece, and this no doubt represents the judgment of common sense upon such arguments. Yet, if collections of things were things, his contention would be irrefragable. It is only because the bay horse and the dun cow taken together are not a new thing that we can escape the conclusion that there are 3 things wherever there are 2. When it is admitted that classes are not things, the question arises, what do we mean by statements which are nominally about classes? Take such a statement as, the class of people interested in mathematical logic is not very numerous. Obviously, this reduces itself to, not very many people are interested in mathematical logic. For the sake of definiteness, let us substitute some particular number, say 3, for very many. Then our statement is, not 3 people are interested in mathematical logic. This may be expressed in the form, if x is interested in mathematical logic, and also y is interested, and also z is interested, then x is identical with y, or x is identical with z, or y is identical with z. Here there is no longer any reference at all to a class. In some such way, all statements nominally about a class can be reduced to statements about what follows from the hypothesis of anything's having the defining property of the class. All that is wanted, therefore, in order to render the verbal use of classes legitimate, is a uniform method of interpreting propositions in which such a use occurs, so as to obtain propositions in which there is no longer any such use. The definition of such a method is a technical matter, which Dr. Whitehead and I have dealt with elsewhere, and which we need not enter into on this occasion. Footnote 1. Confer Principia Mathematica, Star 20, and Introduction, Chapter 3. End of footnote 1. If the theory that classes are merely symbolic is accepted, it follows that numbers are not actual entities, but that propositions in which numbers verbally occur have not really any constituents corresponding to numbers, but only a certain logical form, which is not a part of propositions having this form. This is in fact the case with all the apparent objects of logic and mathematics. Such words as or, not, if, there is, identity, greater, plus, nothing, everything, function, and so on, are not names of definite objects, like John or Jones, but are words which require a context in order to have meaning. All of them are formal, that is to say, their occurrence indicates a certain form of proposition, not a certain constituent. Logical constants, in short, are not entities. The words expressing them are not names, and cannot significantly be made into logical subjects, except when it is the words themselves, as opposed to their meanings, that are being discussed. Footnote 1. See Tractatus Logica Philosophicus by Ludwig Wittgenstein, Kegan-Paul, 1922. End of footnote 1. This fact has a very important bearing on all logic and philosophy, since it shows how they differ from the special sciences. But the questions raised are so large and so difficult that it is impossible to pursue them further on this occasion. End of Lecture 7. Lecture 8 of Our Knowledge of the External World as a Field for Scientific Method in Philosophy by Bertrand Russell. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Landon D. Elkind at the University of Iowa, in Iowa City, Iowa. On the notion of cause with applications to the free will problem. The nature of philosophic analysis, as illustrated in our previous lectures, can now be stated in general terms. We start from a body of common knowledge, which constitutes our data. On examination, the data are found to be complex, rather vague, and largely interdependent logically. By analysis, we reduce them to propositions, which are, as nearly as possible, simple and precise. And we arrange them in deductive chains, in which a certain number of initial propositions form a logical guarantee for all the rest. These initial propositions are premises for the body of knowledge in question. Premises are thus quite different from data. They are simpler, more precise, and less infected with logical redundancy. If the work of analysis has been performed completely, they will be wholly free from logical redundancy, wholly precise, and as simple as is logically compatible with their leading to the given body of knowledge. The discovery of these premises belongs to philosophy, but the work of deducing the body of common knowledge from them belongs to mathematics, if mathematics is interpreted in a somewhat liberal sense. But besides the logical analysis of the common knowledge which forms our data, there is the consideration of its degree of certainty. When we have arrived at its premises, we may find that some of them seem open to doubt, and we may find further that this doubt extends to those of our original data which depend upon these doubtful premises. In our third lecture, for example, we saw that the part of physics which depends upon testimony, and thus upon the existence of other minds than our own, does not seem so certain as the part which depends exclusively upon our own sense data and the laws of logic. Similarly, it used to be felt that the parts of geometry which depend upon the axiom of parallels have less certainty than the parts which are independent of this premise. We may say generally that what commonly passes as knowledge is not at all equally certain, and that when analysis into premises has been effected, the degree of certainty of any consequence of the premises will depend upon that of the most doubtful premise employed in proving this consequence. Thus, analysis into premises serves not only a logical purpose, but also the purpose of facilitating an estimate as to the degree of certainty to be attached to this or that derivative belief. In view of the fallibility of all human beliefs, this service seems at least as important as the purely logical services rendered by philosophical analysis. In the present lecture, I wish to apply the analytic method to the notion of cause, and to illustrate the discussion by applying it to the problem of free will. For this purpose, I shall inquire: 1. What is meant by a causal law? 2. What is the evidence that causal laws have held hitherto? 3. What is the evidence that they will continue to hold in the future? 4. How the causality which is used in science differs from that of common sense and traditional philosophy. 5. What new light is thrown on the question of free will by our analysis of the notion of cause? 1. By a causal law, I mean any general proposition in virtue of which it is possible to infer the existence of one thing or event from the existence of another or of a number of others. If you hear thunder without having seen lightning, you infer that there nevertheless was a flash, because of the general proposition, all thunder is preceded by lightning. When Robinson Crusoe sees a footprint, he infers a human being, and he might justify his inference by the general proposition, all marks in the ground shaped like a human foot are subsequent to a human being's standing where the marks are. When we see the sun set, we expect that it will rise again the next day. When we hear a man speaking, we infer that he has certain thoughts. All these inferences are due to causal laws. A causal law, we said, allows us to infer the existence of one thing or event from the existence of one or more others. The word thing here is to be understood as only applying to particulars, that is, as excluding such logical objects as numbers or classes or abstract properties or relations, and including sense data, with whatever is logically of the same type as sense data. Footnote 1. Thus, we are not using thing here in the sense of a class of correlated aspects as we did in Lecture 3. Each aspect will count separately in stating causal laws. End of footnote 1. Insofar as a causal law is directly verifiable, the thing inferred from the thing from which it is inferred must both be data, though they need not both be data at the same time. In fact, a causal law which is being used to extend our knowledge of existence must be applied to what, at the moment, is not a datum. It is in the possibility of such application that the practical utility of a causal law consists. The important point for our purposes, however, is that what is inferred is a thing, a particular, an object having the kind of reality that belongs to objects of sense, not an abstract object such as virtue or the square root of 2. But we cannot become acquainted with a particular except by its being actually given. Hence, the particular inferred by a causal law must only be described with more or less exactness. It cannot be named until the inference is verified. Moreover, since the causal law is general and capable of applying to many cases, the given particular from which we infer must allow the inference in virtue of some general characteristic, not in virtue of its being just the particular that it is. This is obvious in all our previous instances. We infer the unperceived lightning from the thunder, not in virtue of any peculiarity of the thunder, but in virtue of its resemblance to other claps of thunder. Thus, a causal law must state that the existence of a thing of a certain sort, or of a number of things of a number of assigned sorts, implies the existence of another thing having a relation to the first, which remains invariable so long as the first is of the kind in question. It is to be observed that what is constant in a causal law is not the object or objects given, nor yet the object inferred, both of which may vary within wide limits, but the relation between what is given and what is inferred. The principle same cause, same effect, which is sometimes said to be the principle of causality, is much narrower in its scope than the principle which really occurs in science. Indeed, if strictly interpreted, it has no scope at all, since the same cause never recurs exactly. We shall return to this point at a later stage of the discussion. The particular which is inferred may be uniquely determined by the causal law, or may be only described in such general terms that many different particulars might satisfy the description. This depends upon whether the constant relation affirmed by the causal law is one which only one term can have to the data, or one which many terms may have. If many terms may have the relation in question, science will not be satisfied until it has found some more stringent law, which will enable us to determine the inferred things uniquely. Since all known things are in time, a causal law must take account of temporal relations. It will be part of the causal law to state a relation of succession or coexistence between the thing given and the thing inferred. When we hear thunder and infer that there was lightning, the law states that the thing inferred is earlier than the thing given. Conversely, when we see lightning and wait expectantly for the thunder, the law states that the thing given is earlier than the thing inferred. When we infer a man's thoughts from his words, the law states that the two are, at least approximately, simultaneous. If a causal law is to achieve the precision at which science aims, it must not be content with a vague earlier or later, but must state how much earlier or how much later. That is to say, the time relation between the thing given and the thing inferred ought to be capable of exact statement, and usually the inference to be drawn is different according to the length and direction of the interval. A quarter of an hour ago this man was alive, an hour hence he will be cold. Such a statement involves two causal laws, one inferring from a datum something which existed a quarter of an hour ago, the other inferring from the same datum something which will exist an hour hence. Often a causal law involved not one datum, but many, which need not be all simultaneous with each other, though their time relations must be given. The general scheme of a causal law will be as follows. Whenever things occur in certain relations to each other, among which their time relations must be included, then a thing having a fixed relation to these things will occur at a date fixed relatively to their dates. The things given will not in practice be things that only exist for an instant, for such things, if there are any, can never be data. The things given will each occupy some finite time. They may not be static things, but processes, especially motions. We have considered in an earlier lecture the sense in which a motion may be a datum, and need not now recur to this topic. It is not essential to a causal law that the object inferred should be later than some or all of the data. It may equally well be earlier or at the same time. The only thing essential is that the law should be such as to enable us to infer the existence of an object which we can more or less accurately describe in terms of the data. 2. I come now to our second question, namely, what is the nature of the evidence that causal laws have held hitherto, at least in the observed portions of the past? This question must not be confused with the further question, does this evidence warrant us in assuming the truth of causal laws in the future and in unobserved portions of the past? For the present, I am only asking what are the grounds which lead to a belief in causal laws, not whether these grounds are adequate to support the belief in universal causation. The first step is the discovery of approximate unanalyzed uniformities of sequence or coexistence. After lightning comes thunder, after a blow received comes pain, after approaching a fire comes warmth. Again, there are uniformities of coexistence, for example, between touch and sight, between certain sensations in the throat and the sound of one's voice, and so on. Every such uniformity of sequence or coexistence, after it has been experienced a certain number of times, is followed by an expectation that it will be repeated on future occasions, i.e., that where one of the correlated events is found, the other will be found also. The connection of experienced past uniformity with expectation as to the future is just one of those uniformities of sequence, which we have observed to be true hitherto. This affords a psychological account of what may be called the animal belief in causation, because it is something which can be observed in horses and dogs, and is rather a habit of acting than a real belief. So far, we have merely repeated Hume, who carried the discussion of cause up to this point, but did not, apparently, perceive how much remained to be said. Is there, in fact, any characteristic, such as might be called causality or uniformity, which is found to hold throughout the observed past? And if so, how is it to be stated? The particular uniformities which we mentioned before, such as lightning being followed by thunder, are not found to be free from exceptions. We sometimes see lightning without hearing thunder, and although, in such a case, we suppose that thunder might have been heard if we had been nearer to the lightning, that is a supposition based on theory, and therefore incapable of being invoked to support the theory. What does seem, however, to be shown by scientific experience is this, that where an observed uniformity fails, some wider uniformity can be found, embracing more circumstances and subsuming both the successes and the failures of the previous uniformity. Unsupported bodies in air fall, unless they are balloons or aeroplanes, but the principles of mechanics give uniformities which apply to balloons and aeroplanes just as accurately as to bodies that fall. There is much that is hypothetical and more or less artificial in the uniformities affirmed by mechanics, because, when they cannot otherwise be made applicable, unobserved bodies are inferred in order to account for observed peculiarities. Still, it is an empirical fact that it is possible to preserve the laws by assuming such bodies, and that they never have to be assumed in circumstances in which they ought to be observable. Thus, the empirical verification of mechanical laws may be admitted, although we must also admit that it is less complete and triumphant than is sometimes supposed. Assuming now, what must be admitted to be doubtful, that the whole of the past has proceeded according to invariable laws, what can we say as to the nature of these laws? They will not be of the simple type which asserts that the same cause always produces the same effect. We may take the law of gravitation as a sample of the kind of law that appears to be verified without exception. In order to state this law in a form which observation can confirm, we will confine it to the solar system. It then states that the motions of planets and their satellites have at every instant an acceleration compounded of accelerations towards all the other bodies in the solar system, proportional to the matters of these bodies and inversely proportional to the squares of their distances. In virtue of this law, given the state of the solar system throughout any finite time, however short, its state at all earlier and later times is determinate, except in so far as other forces than gravitation or other bodies than those in the solar system have to be taken into consideration. But other forces, so far as science can discover, appear to be equally regular, and equally capable of being summed up in single causal laws. If the mechanical account of matter were complete, the whole physical history of the universe, past and future, could be inferred from a sufficient number of data concerning an assigned finite time, however short. In the mental world, the evidence for the universality of causal laws is less complete than in the physical world. Psychology cannot boast of any triumph comparable to gravitational astronomy. Nevertheless, the evidence is not very greatly less than in the physical world. The crude and approximate causal laws from which science starts are just as easy to discover in the mental sphere as in the physical. In the world of sense, there are, to begin with, the correlations of sight and touch, and so on, and the facts which lead us to connect various kinds of sensations with eyes, ears, nose, tongue, and so on. Then there are such facts as that our body moves in answer to our volitions. Exceptions exist, but are capable of being explained as easily as the exceptions to the rule that unsupported bodies in air fall. There is, in fact, just such a degree of evidence for causal laws in psychology as will warrant the psychologist in assuming them as a matter of course, though not such a degree as will suffice to remove all doubt from the mind of a sceptical inquirer. It should be observed that causal laws in which the given term is mental and the inferred term physical, or vice versa, are at least as easy to discover as causal laws in which both terms are mental. It will be noticed that, although we have spoken of causal laws, we have not hitherto introduced the word cause. At this stage, it will be well to say a few words on legitimate and illegitimate uses of this word. The word cause in the scientific account of the world belongs only to the early stages, in which small, preliminary, approximate generalizations are being ascertained with a view to subsequent larger and more invariable laws. There is, however, a somewhat rough and loose use of the word cause which may be preserved. The approximate uniformities which lead to its pre-scientific employment may turn out to be true in all but very rare and exceptional circumstances, perhaps in all circumstances that actually occur. In such cases, it is convenient to be able to speak of the antecedent event as the cause, and the subsequent event as the effect. In this sense, provided it is realised that the sequence is not necessary and may have exceptions, it is still possible to employ the words cause and effect. It is in this sense, and in this sense only, that we shall intend the words when we speak of one particular event causing another particular event, as we must sometimes do if we are to avoid intolerable circumlocution. 3. We come now to our third question, namely, what reason can be given for believing that causal laws will hold in the future, or that they have held in unobserved portions of the past? What we have said so far is that there have been hitherto certain observed causal laws, and that all empirical evidence we possess is compatible with the view that everything, both mental and physical, so far as our observation has extended, has happened in accordance with causal laws. The law of universal causation suggested by these facts may be enunciated as follows. There are such invariable relations between different events at the same or different times that, given the state of the whole universe throughout any finite time, however short, every previous and subsequent event can theoretically be determined as a function of the given events during that time. Have we any reason to believe this universal law? Or, to ask a more modest question, have we any reason to believe that a particular causal law, such as the law of gravitation, will continue to hold in the future? Among observed causal laws is this, that observation of uniformities is followed by expectation of their recurrence. A horse who has been driven always along a certain road expects to be driven along that road again. A dog who is always fed at a certain hour expects food at that hour and not at any other. Such expectations, as Hume pointed out, explain only too well the common sense belief in uniformities of sequence, but they afford absolutely no logical ground for beliefs as to the future, not even for belief that we shall continue to expect the continuation of experienced uniformities. For that is precisely one of those causal laws for which a ground has to be sought. If Hume's account of causation is the last word, we have not only no reason to suppose that the sun will rise tomorrow, but no reason to suppose that 5 minutes hence we shall still expect it to rise tomorrow. It may, of course, be said that all inferences as to the future are in fact invalid, and I do not see how such a view could be disproved. But while admitting the legitimacy of such a view, we may nevertheless inquire, if inferences as to the future are valid, what principle must be involved in making them? The principle involved is the principle of induction. Footnote 1. On this subject, see Keynes's Treatise on Probability, Macmillan, 1921. End of footnote 1. Which, if it is true, must be an a priori logical law, not capable of being proved or disproved by experience. It is a difficult question how this principle ought to be formulated, but if it is to warrant the inferences which we wish to make by its means, it must lead to the following proposition. If in a great number of instances a thing of a certain kind is associated in a certain way with a thing of a certain other kind, it is probable that a thing of the one kind is always similarly associated with a thing of the other kind, and as the number of instances increases, the probability approaches indefinitely near to certainty. It may well be questioned whether this proposition is true, but if we admit it, we can infer that any characteristic of the whole of the observed past is likely to apply to the future and to the unobserved past. This proposition, therefore, if it is true, will warrant the inference that causal laws probably hold at all times, future as well as past. But without this principle, the observed cases of the truth of causal laws afford no presumption as to the unobserved cases, and therefore the existence of a thing not directly observed can never be validly inferred. It is thus the principle of induction, rather than the law of causality, which is at the bottom of all inferences as to the existence of things not immediately given. With the principle of induction, all that is warranted for such inferences can be proved. Without it, all such inferences are invalid. This principle has not received the attention which its great importance deserves. Those who were interested in deductive logic naturally enough ignored it, while those who emphasised the scope of induction wished to maintain that all logic is empirical, and therefore could not be expected to realise that induction itself, their own darling, required a logical principle which obviously could not be proved inductively, and must therefore be a priori, if it could be known at all. The view that the law of causality itself is a priori cannot, I think, be maintained by anyone who realises what a complicated principle it is. In the form which states that every event has a cause, it looks simple, but on examination, cause is merged into causal law, and the definition of a causal law is found to be far from simple. There must necessarily be some a priori principle involved in inference from the existence of one thing to that of another, if such inference is ever valid. But it would appear from the above analysis that the principle in question is induction, not causality. Whether inferences from past to future are valid depends wholly, if our discussion has been sound, upon the inductive principle. If it is true, such inferences are valid, and if it is false, they are invalid. 4. I come now to the question how the conception of causal laws, which we arrived at, is related to the traditional conception of cause as it occurs in philosophy and common sense. Historically, the notion of cause has been bound up with that of human volition. The typical cause would be the fiat of a king. The cause is supposed to be active, the effect passive. From this, it is easy to pass on to the suggestion that a true cause must contain some prevision of the effect. Hence the effect becomes the end at which the cause aims, and teleology replaces causation in the explanation of nature. But all such ideas, as applied to physics, are mere anthropomorphic superstitions. It is as a reaction against these errors that Mach and others have urged a purely descriptive view of physics. Physics, they say, does not aim at telling us why things happen, but only how they happen. And if the question why means anything more than the search for a general law according to which a phenomenon occurs, then it is certainly the case that this question cannot be answered in physics, and ought not to be asked. In this sense, the descriptive view is indubitably in the right. But in using causal laws to support inferences from the observed to the unobserved, physics ceases to be purely descriptive, and it is these laws which give the scientifically useful part of the traditional notion of cause. There is therefore something to preserve in this notion, though it is a very tiny part of what is commonly assumed in orthodox metaphysics. In order to understand the difference between the kind of cause which science uses and the kind which we naturally imagine, it is necessary to shut out, by an effort, everything that differentiates between past and future. This is an extraordinarily difficult thing to do, because our mental life is so intimately bound up with difference. Not only do memory and hope make a difference in our feelings as regard past and future, but almost our whole vocabulary is filled with the idea of activity, of things done now for the sake of their future effects. All transitive verbs involve the notion of cause as activity, and would have to be replaced by some cumbrous periphrases before this notion could be eliminated. Consider such a statement as Brutus killed Caesar. On another occasion, Brutus and Caesar might engage our attention, but for the present it is the killing that we have to study. We may say that to kill a person is to cause his death intentionally. This means that desire for a person's death causes a certain act, because it is believed that that act will cause the person's death. Or, more accurately, the desire and the belief jointly cause the act. Brutus desires that Caesar should be dead, and believes that he will be dead if he is stabbed. Brutus therefore stabs him, and the stab causes Caesar's death, as Brutus expected it would. Every act which realizes a purpose involves two causal steps in this way. C is desired, and it is believed, truly if the purpose is achieved, that B will cause C. The desire and this belief together cause B, which in turn causes C. Thus we have first A, which is a desire for C, and a belief that B, an act, will cause C. Then we have B, the act caused by A and believed to be a cause of C. Then, if the belief was correct, we have C, caused by B, and if the belief was incorrect, we have disappointment. Regarded purely scientifically, this series A, B, C may equally well be considered in the inverse order, as they would be at a coroner's inquest. But from the point of view of Brutus, the desire which comes at the beginning is what makes the whole series interesting. We feel that if his desires had been different, the effects which he had in fact produced would not have occurred. This is true and gives him a sense of power and freedom. It is equally true that if the effects had not occurred, his desires would have been different, since being what they were, the effects did occur. Thus, the desires are determined by their consequences just as much as the consequences by their desires. But as we cannot in general know in advance the consequences of our desires without knowing our desires, this form of inference is uninteresting as applied to our own acts, though quite vital as applied to those of others. A cause, considered scientifically, has none of that analogy with volition which makes us imagine that the effect is compelled by it. A cause is an event or group of events of some known general character, and having a known relation to some other event, called the effect, the relation being of such a kind that only one event, or at any rate only one well-defined sort of event, can have the relation to a given cause. It is customary only to give the name effect to an event which is later than the cause. But there is no kind of reason for this restriction. We shall do better to allow the effect to be before the cause, or simultaneous with it, because nothing of any scientific importance depends upon its being after the cause. If the inference from cause to effect is to be indubitable, it seems that the cause can hardly stop short of the whole universe. So long as anything is left out, something may be left out which alters the expected result. But for practical and scientific purposes, phenomena can be collected into groups, which are causally self-contained or nearly so. In the common notion of causation, the cause is a single event. We say the lightning causes the thunder, and so on. But it is difficult to know what we mean by a single event, and it generally appears that, in order to have anything approaching certainty concerning the effect, it is necessary to include many more circumstances in the cause than unscientific common sense would suppose. But often a probable causal connection, where the cause is fairly simple, is of more practical importance than a more indubitable connection in which the cause is so complex as to be hard to ascertain. To sum up, the strict, certain, universal law of causation which philosophers advocate is an ideal, possibly true, but not known to be true in virtue of any available evidence. What is actually known as a matter of empirical science is that certain constant relations are observed to hold between the members of a group of events at certain times, and that when such relations fail, as they sometimes do, it is usually possible to discover a new, more constant relation by enlarging the group. Any such constant relation between events of specified kinds, with given intervals of time between them, is a causal law. But all causal laws are liable to exceptions if the cause is less than the whole state of the universe. We believe exceptions can be dealt with by enlarging the group we call the cause, but this belief, wherever it is still unverified, ought not to be regarded as certain, but only as suggesting a direction for further inquiry. A very common causal group consists of volitions and the consequent bodily acts, though exceptions arise, for example, through sudden paralysis. Another very frequent connection, though here the exceptions are much more numerous, is between a bodily act and the realization of the purpose which led to the act. These connections are patent, whereas the causes of desires are more obscure. Thus it is natural to begin causal series with desires, and to suppose that all causes are analogous to desires, and that desires themselves arise spontaneously. Such a view, however, is not one which any serious psychologist would maintain. But this brings us to the question of the application of our analysis of cause to the problem of free will. 5. The problem of free will is so intimately bound up with the analysis of causation that, old as it is, we need not despair of obtaining new light on it by the help of new views on the notion of cause. The free will problem has, at one time or another, stirred men's passions profoundly, and the fear that the will might not be free has been to some men a source of great unhappiness. I believe that, under the influence of a cool analysis, the doubtful questions involved will be found to have no such emotional importance as is sometimes thought, since the disagreeable consequences supposed to flow from a denial of free will do not flow from this denial in any form in which there is reason to make it. It is not, however, on this account chiefly that I wish to discuss this problem, but rather because it affords a good example of the clarifying effect of analysis and of the interminable controversies which may result from its neglect. Let us first try to discover what it is we really desire when we desire free will. Some of our reasons for desiring free will are profound, some trivial. To begin with the former, We do not wish to feel ourselves in the hands of fate, so that, however much we may desire to will one thing, we may nevertheless be compelled by an outside force to will another. We do not wish to think that, however much we may desire to act well, hereditary and surroundings may force us into acting ill. We wish to feel that, in cases of doubt, our choice is momentous and lies within our power. Besides these desires, which are worthy of all respect, we have, however, others not so respectable, which equally make us desire free will. We do not like to think that other people, if they knew enough, could predict our actions, though we know that we can often predict those of other people, especially if they are elderly. Much as we esteem the old gentleman who is our neighbour in the country, we know that when grouse are mentioned, he will tell the story of the grouse in the gun-room. But we ourselves are not so mechanical. We never tell an anecdote to the same person twice, or even once, unless he is sure to enjoy it. Although we once met, say, Bismarck, we are quite capable of hearing him mentioned without relating the occasion when we met him. In this sense, everybody thinks that he himself has free will, though he knows that no one else has. The desire for this kind of free will seems to be no better than a form of vanity. I do not believe that this desire can be gratified with any certainty, but the other more respectable desires are, I believe, not inconsistent with any tenable form of determinism. We have thus two questions to consider. 1. Are human actions theoretically predictable from a sufficient number of antecedents? 2. Are human actions subject to an external compulsion? The two questions, as I shall try to show, are entirely distinct, and we may answer the first in the affirmative without therefore being forced to give an affirmative answer to the second. 1. Are human actions theoretically predictable from a sufficient number of antecedents? Let us first endeavour to give precision to this question. We may state the question thus: is there some constant relation between an act and a certain number of earlier events, such that, when the earlier events are given, only one act, or at most only acts with some well-marked character, can have this relation to the earlier events? If this is the case, then, as soon as the earlier events are known, it is theoretically possible to predict either the precise act, or at least the character necessary to its fulfilling the constant relation. To this question a negative answer has been given by Bergson, in a form which calls in question the general applicability of the law of causation. He maintains that every event, and more particularly every mental event, embodies so much of the past that it could not possibly have occurred at any earlier time, and is therefore necessarily quite different from all previous and subsequent events. If, for example, I read a certain poem many times, my experience on each occasion is modified by the previous readings, and my emotions are never repeated exactly. The principle of causation, according to him, asserts that the same cause, if repeated, will produce the same effect. But owing to memory, he contends, this principle does not apply to mental events. What is apparently the same cause, if repeated, is modified by the mere fact of repetition, and cannot produce the same effect. He infers that every mental event is a genuine novelty, not predictable from the past, because the past contains nothing exactly like it, by which we could imagine it. And on this ground he regards the freedom of the will as unassailable. Bergson's contention has undoubtedly a great deal of truth, and I have no wish to deny its importance. But I do not think its consequences are quite what he believes them to be. It is not necessary for the determinist to maintain that he can foresee the whole particularity of the act which will be performed. If he could foresee that A was going to murder B, his foresight would not be invalidated by the fact that he could not know all the infinite complexity of A's state of mind in committing the murder, nor whether the murder was to be performed with a knife or with a revolver. If the kind of act which will be performed can be foreseen within narrow limits, it is of little practical interest that there are fine shades which cannot be foreseen. No doubt every time the story of the grouse in the gunroom is told, there will be slight differences due to increasing habitualness, but they will not invalidate the prediction that the story will be told. And there is nothing in Bergson's argument to show that we can never predict what kind of act will be performed. Again, his statement of the law of causation is inadequate. The law does not state merely that, if the same cause is repeated, the same effect will result. It states rather that there is a constant relation between causes of certain kinds and effects of certain kinds. For example, if a body falls freely, there is a constant relation between the height through which it falls and the time it takes in falling. It is not necessary to have a body fall through the same height which has been previously observed in order to be able to foretell the length of time occupied in falling. If this were necessary, no prediction would be possible, since it would be impossible to make the height exactly the same on two occasions. Similarly, the attraction which the sun will exert on the earth is not only known at distances for which it has been observed, but at all distances, because it is known to vary as the inverse square of the distance. In fact, what is found to be repeated is always the relation of cause and effect, not the cause itself. All that is necessary as regards the cause is that it should be of the same kind, in the relevant respect, as earlier causes whose effects have been observed. Another respect in which Bergson's statement of causation is inadequate is in its assumption that the cause must be one event, whereas it may be two or more events, or even some continuous process. The substantive question at issue is whether mental events are determined by the past. Now, in such a case as the repeated reading of a poem, it is obvious that our feelings in reading the poem are most emphatically dependent upon the past, but not upon one single event in the past. All our previous readings of the poem must be included in the cause, but we easily perceive a certain law according to which the effect varies as the previous readings increase in number, and in fact Bergson himself tacitly assumes such a law. We decide at last not to read the poem again, because we know that this time the effect would be boredom. We may not know all the niceties and shades of the boredom we should feel, but we know enough to guide our decision, and the prophecy of boredom is nonetheless true for being more or less general. Thus, the kinds of cases upon which Bergson relies are insufficient to show the impossibility of prediction in the only sense in which prediction has practical or emotional interest. We may therefore leave the consideration of his arguments and address ourselves to the problem directly. The law of causation, according to which later events can theoretically be predicted by means of earlier events, has often been held to be a priori, a necessity of thought, a category without which science would be impossible. These claims seem to me excessive. In certain directions, the law has been verified empirically, and in other directions there is no positive evidence against it. But science can use it where it has been found to be true, without being forced into any assumption as to its truth in other fields. We cannot therefore feel any a priori certainty that causation must apply to human volitions. The question how far human volitions are subject to causal laws is a purely empirical one. Empirically, it seems plain that the great majority of our volitions have causes, but it cannot on this account be held necessarily certain that all have causes. There are, however, precisely the same kinds of reasons for regarding it as probable that they all have causes as there are in the case of physical events. We may suppose, though this is doubtful, that there are laws of correlation of the mental and the physical, in virtue of which, given the state of all the matter in the world, and therefore of all the brains and living organisms, the state of all the minds in the world could be inferred, while conversely, the state of all the matter in the world could be inferred if the state of all the minds were given. it is obvious that there is some degree of correlation between brain and mind, and it is impossible to say how complete it may be. This, however, is not the point which I wish to elicit. What I wish to urge is that, even if we admit the most extreme claims of determinism and of correlation of mind and brain, still the consequences inimical to what is worth preserving in free will do not follow. The belief that they follow results, I think, entirely from the assimilation of causes to volitions, and from the notion that causes compel their effects in some sense analogous to that in which a human authority can compel a man to do what he would rather not do. This assimilation, as soon as the true nature of scientific causal laws is realized, is seen to be a sheer mistake. But this brings us to the second of the two questions which we raised in regard to free will, namely, whether, assuming determinism, our actions can be in any proper sense regarded as compelled by outside forces. 2. Are human actions subject to an external compulsion? We have in deliberation a subjective sense of freedom, which is sometimes alleged against the view that volitions have causes. This sense of freedom, however, is only a sense that we can choose which we please of a number of alternatives. It does not show us that there is no causal connections between what we please to choose and our previous history. The supposed inconsistency of these two springs from the habit of conceiving causes as analogous to volitions, a habit which often survives unconsciously in those who intend to conceive causes in a more scientific manner. If a cause is analogous to a volition, outside causes will be analogous to an alien will, and acts predictable from outside causes will be subject to compulsion. But this view of cause is one to which science lends no countenance. Causes, we have seen, do not compel their effects any more than effects compel their causes. There is a mutual relation, so that either can be inferred from the other. When the geologist infers the past state of the earth from its present state, we should not say the present state compels the past state to have been what it was. Yet it renders it necessary as a consequence of the data, in the only sense in which effects are rendered necessary by their causes. The difference which we feel in this respect between causes and effects is a mere confusion, due to the fact that we remember past events, but do not happen to have memory of the future. The apparent indeterminateness of the future, upon which some advocates of free will rely, is merely a result of our ignorance. It is plain that no desirable kind of free will can be dependent simply upon our ignorance. For if that were the case, animals would be more free than men, and savages than civilized people. Free will, in any valuable sense, must be compatible with the fullest knowledge. Now, quite apart from any assumption as to causality, it is obvious that complete knowledge would embrace the future as well as the past. Our knowledge of the past is not wholly based upon causal inferences, but is partly derived from memory. It is a mere accident that we have no memory of the future. We might, as in the pretended visions of seers, see future events immediately, in the way in which we see past events. They certainly will be what they will be, and are in this sense just as determined as the past. If we saw future events in the same immediate way in which we see past events, what kind of free will would still be possible? Such a kind would be wholly independent of determinism. It could not be contrary to even the most entirely universal reign of causality. And such a kind must contain whatever is worth having in free will, since it is impossible to believe that mere ignorance can be the essential condition of any good thing. Let us therefore imagine a set of beings who know the whole future with absolute certainty, and let us ask ourselves whether they could have anything that we should call free will. Such beings as we are imagining would not have to wait for the event in order to know what decision they were going to adopt on some future occasion. They would know now what their volitions were going to be. But would they have any reason to regret this knowledge? Surely not, unless the foreseen volitions were in themselves regrettable. It is less likely that the foreseen volitions would be regrettable if the steps which would lead to them were also foreseen. It is difficult not to suppose that what is foreseen is fated, and must happen however much it may be dreaded. But human actions are the outcome of desire, and no foreseeing can be true unless it takes account of desire. A foreseen volition will have to be one which does not become odious through being foreseen. The beings we are imagining would easily come to know the causal connections of volitions, and therefore their volitions would be better calculated to satisfy their desires than ours are. Since volitions are the outcome of desires, a prevision of volitions contrary to desires could not be a true one. It must be remembered that the supposed prevision would not create the future any more than memory creates the past. We do not think we were necessarily not free in the past, merely because we can now remember our past volitions. Similarly, we might be free in the future, even if we could now see what our future volitions were going to be. Freedom, in short, in any valuable sense, demands only that our volitions shall be, as they are, the result of our own desires, not of an outside force compelling us to will what we would rather not will. Everything else is confusion of thought, due to the feeling that knowledge compels the happening of what it knows when this is future, though it is at once obvious that knowledge has no such power in regard to the past. Free will, therefore, is true in the only form which is important, and the desire for other forms is a mere effect of insufficient analysis. What has been said on philosophical method in the foregoing lectures has been rather by means of illustrations in particular cases than by means of general precepts. Nothing of any value can be said on method except through examples. But now, at the end of our course, we may collect certain general maxims which may possibly be a help in acquiring a philosophical habit of mind and a guide in looking for solutions of philosophic problems. Philosophy does not become scientific by making use of other sciences in the kind of way in which, for example, Herbert Spencer does. Philosophy aims at what is general, and the special sciences, however they may suggest large generalizations, cannot make them certain, and a hasty generalization, such as Spencer's generalization of evolution, is none the less hasty because what is generalized is the latest scientific theory. Philosophy is a study apart from the other sciences. Its results cannot be established by the other sciences, and conversely must not be such as some other science might conceivably contradict. Prophecies as to the future of the universe, for example, are not the business of philosophy. Whether the universe is progressive, retrograde, or stationary is not for the philosopher to say. In order to become a scientific philosopher, a certain peculiar mental discipline is required. There must be present, first of all, the desire to know philosophical truth, and this desire must be sufficiently strong to survive through years when there seems no hope of its finding any satisfaction. The desire to know philosophical truth is very rare. In its purity, it is not often found even among philosophers. It is obscured sometimes, particularly after long periods of fruitless search, by the desire to think we know. Some plausible opinion presents itself, and by turning our attention away from the objections to it, or merely by not making great efforts to find objections to it, we may obtain the comfort of believing it, although if we had resisted the wish for comfort, we should have come to see that the opinion was false. Again, the desire for unadulterated truth is often obscured in professional philosophers by love of system. The one little fact which will not come inside the philosopher's edifice has to be pushed and tortured until it seems to consent. Yet the one little fact is more likely to be important for the future than the system with which it is inconsistent. Pythagoras invented a system which fitted admirably with all the facts he knew, except the incommensurability of the diagonal of a square in the side. This one little fact stood out, and remained a fact, even after Hippasos of Metapontion was drowned for revealing it. To us, the discovery of this claim is the chief claim of Pythagoras to immortality, while his system has become a matter of merely historical curiosity. Footnote 1. The above remarks, for purposes of illustration, adopt one of several possible opinions on each of several disputed points. End of footnote 1. Love of system, therefore, and the system-maker's vanity which becomes associated with it, are among the snares that the student of philosophy must guard against. The desire to establish this or that result, or generally to discover evidence for agreeable results of whatever kind, has of course been the chief obstacle to honest philosophizing. So strangely perverted do men become by unrecognized passions that a determination in advance to arrive at this or that conclusion is generally regarded as a mark of virtue, and those whose studies lead to an opposite conclusion are thought to be wicked. No doubt it is commoner to wish to arrive at an agreeable result than to wish to arrive at a true result. But only those in whom the desire to arrive at a true result is paramount can hope to serve any good purpose by the study of philosophy. But even when the desire to know exists in the requisite strength, the mental vision by which abstract truth is recognized is hard to distinguish from vivid imaginability and consonance with mental habits. It is necessary to practice methodological doubt, like Descartes, in order to loosen the hold of mental habits, and it is necessary to cultivate logical imagination, in order to have a number of hypotheses at command, and not to be the slave of the one which common sense has rendered easy to imagine. These two processes of doubting the familiar and imagining the unfamiliar are correlative, and form the chief part of the mental training required for a philosopher. The naive beliefs which we find in ourselves when we first begin the process of philosophic reflection may turn out, in the end, to be almost all capable of a true interpretation, but they ought all, before being admitted into philosophy, to undergo the ordeal of sceptical criticism. Until they have gone through this ordeal, they are mere blind habits, ways of behaving rather than intellectual convictions. And although it may be that a majority will pass the test, we may be pretty sure that some will not, and that a serious readjustment of our outlook ought to result. In order to break the dominion of habit, we must do our best to doubt the senses, reason, morals, everything, in short. In some directions, doubt will be found possible, in others it will be checked by that direct vision of abstract truth upon which the possibility of philosophical knowledge depends. At the same time, and as an essential aid to the direct perception of truth, it is necessary to acquire fertility in imagining abstract hypotheses. This is, I think, what has most of all been lacking hitherto in philosophy. So meagre was the logical apparatus that all the hypotheses philosophers could imagine were found to be inconsistent with the facts. Too often this state of things led to the adoption of heroic measures, such as a wholesale denial of the facts, when an imagination better stocked with logical tools would have found a key to unlock the mystery. It is in this way that the study of logic becomes the central study in philosophy. It gives the method of research in philosophy, just as mathematics gives the method in physics. And as physics, which, from Plato to the Renaissance, was as unprogressive, dim, and superstitious as philosophy, became a science through Galileo's fresh observation of facts and subsequent mathematical manipulation, so philosophy in our own day is becoming scientific through the simultaneous acquisition of new facts and logical methods. In spite, however, of the new possibility of progress in philosophy, the first effect, as in the case of physics, is to diminish very greatly the extent of what is thought to be known. Before Galileo, people believed themselves possessed of immense knowledge on all the most interesting questions in physics. He established certain facts as to the way in which bodies fall, not very interesting on their own account, but of quite immeasurable interest as examples of real knowledge and of a new method whose future fruitfulness he himself divined. But his new facts sufficed to destroy the whole vast system of supposed knowledge handed down from Aristotle, as even the palest morning sun suffices to extinguish the stars. So in philosophy, though some have believed one system and others another, almost all have been of opinion that a great deal was known. But all this supposed knowledge in the traditional systems must be swept away, and a new beginning must be made, which we shall esteem fortunate indeed if it can attain results comparable to Galileo's law of falling bodies. By the practice of methodological doubt, if it is genuine and prolonged, a certain humility as to our knowledge is induced. We become glad to know anything in philosophy, however seemingly trivial. Philosophy has suffered from the lack of this kind of modesty. It has made the mistake of attacking the most interesting problems at once, instead of proceeding patiently and slowly, accumulating whatever solid knowledge was attainable, and trusting the great problems to the future. Men of science are not ashamed of what is intrinsically trivial, if its consequences are likely to be important. The immediate outcome of an experiment is hardly ever interesting on its own account. So in philosophy, it is often desirable to expend time and care on matters which, judged alone, might seem frivolous, for it is often only through the consideration of such matters that the greater problems can be appreciated. When our problem has been selected, and the necessary mental discipline has been acquired, the method to be pursued is fairly uniform. The big problems which provoke philosophical inquiry are found on examination to be complex, and to depend upon a number of component problems, usually more abstract than those of which they are the components. It will generally be found that all our initial data, all the facts that we seem to know to begin with, suffer from vagueness, confusion, and complexity. Current philosophical ideas share these defects. It is therefore necessary to create an apparatus of precise conceptions as general and as free from complexity as possible, before the data can be analysed into the kind of premises which philosophy aims at discovering. In this process of analysis, the source of difficulty is tracked further and further back, growing at each stage more abstract, more refined, more difficult to apprehend. Usually it will be found that a number of these extraordinarily abstract questions underlie any one of the big obvious problems. When everything has been done that can be done by method, a stage is reached where only direct philosophic vision can carry matters further. Here only genius will avail. What is wanted, as a rule, is some new effort of logical imagination, some glimpse of a possibility never conceived before, and then the direct perception that this possibility is realised in the case in question. Failure to think of the right possibility leaves insoluble difficulties, balanced arguments pro and con, utter bewilderment and despair. But the right possibility, as a rule, when once conceived, justifies itself swiftly, and by its astonishing power of absorbing apparently conflicting facts. From this point onward, the work of the philosopher is synthetic and comparatively easy. It is in the very last stage of the analysis that the real difficulty consists. Of the prospect of progress in philosophy, it would be rash to speak with confidence. Many of the traditional problems of philosophy, perhaps most of those which have interested a wider circle than that of technical students, do not appear to be soluble by scientific methods. Just as astronomy lost much of its human interest when it ceased to be astrology, so philosophy must lose in attractiveness as it grows less prodigal of promises. But to the large and still growing body of men engaged in the pursuit of science, men who hitherto, not without justification, have turned aside from philosophy with a certain contempt, the new method, successful already in such time-honoured problems as number, infinity, continuity, space and time, should make an appeal which the older methods have wholly failed to make. Physics, with its principle of relativity and its revolutionary investigations into the nature of matter, is feeling the need for that kind of novelty in fundamental hypotheses, which scientific philosophy aims at facilitating. The one and only condition, I believe, which is necessary in order to secure for philosophy in the near future an achievement surpassing all that has hitherto been accomplished by philosophers, is the creation of a school of men with scientific training and philosophical interests, unhampered by the traditions of the past, and not misled by the literary methods of those who copy the ancients in all except their merits. End of Lecture 8, and end of Our Knowledge of the External World as a Field for Scientific Method in Philosophy by Bertrand Russell.